This is a conversation with Jacob Barandes. He is a physicist and philosopher of science, popularly known for his work in quantum theory and indivisible stochastics. He's a lecturer and also the co-director of graduate studies at Harvard University. In this conversation, we discuss realism versus anti-realism, the laws of nature. He provides one of the best explanations of quantum theory, the measurement problem, the Wigner's friend thought experiment, and then we also explore his theory of indivisible stochastics. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and effort. So if you'd like to see it continue, please consider making a donation on Patreon or Anchor. You can buy super thanks on YouTube. You can join as a member on YouTube. You can buy gifts on Instagram Reels. I'm starting to experiment with giving members early access to these videos. So please consider supporting this project if you can. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For the forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now it is no time. If a tree falls in a forest and no one is around, does it make a sound? In the book, Introduction to Quantum Mechanics, David Griffiths provided 3 possible answers to this thought experiment. He said, did the physical system actually have the attribute in question prior to the measurement, the so-called realist position? Or did the act of measurement itself create the property, the orthodox position or the anti-realist position? Or can we duck the question entirely on the grounds that it is metaphysical, the agnostic response? What is the realist position? What is the orthodox position? What is the agnostic position? And when a tree falls in a forest, which of these positions do you think is closest to reality?
Let me just first start by saying again how much of a privilege it is being here with you today. I'm really glad to be talking about this. It's an incredible privilege and honor to spend our time talking about the questions of reality, the questions of nature. It's something that I don't ever take for granted, and it's really a wonderful thing that we get to do this. David Griffiths' book, Introduction to Quantum Mechanics, is widely used among undergraduate students all across the English-speaking world and beyond. The book begins with a conversation about the metaphysics, the questions about reality that underlie physical theories, and in particular that underlie quantum mechanics. Quantum mechanics is a physical framework or theory that aims to describe the results we get when we do measurements on very small systems, on microscopic systems. It does apply to varying degrees to larger than microscopic systems in certain contexts. It's a very mysterious theory. And so it's not shocking that David Griffiths would begin the book by talking a little bit about these sorts of philosophical or metaphysical questions. Yeah. David Griffiths divides up the metaphysical viewpoints he argues one can take about quantum mechanics into the 3 categories you've just listed: the realist position, the orthodox position, and the agnostic position. My feeling is that this trichotomy steamrolls a lot of very important nuances. For example, one can be a realist about some aspects of physical systems, but maybe not a realist about other aspects of physical systems. For example, even in everyday life, we think that the fact that you're sitting on a chair is a real fact. But maybe the things you're imagining right now aren't real facts.
Yeah.
We think that maybe objects around us have mass and volume and locations. We think that maybe they interact with light in certain ways. They absorb certain frequencies of light. They emit other frequencies of light. But our experience of seeing red or brown or green or yellow when looking at objects, I think most people are comfortable with the idea that maybe those color perceptions aren't real in quite the same way that physical objects or their interaction with light may be real. There are some phenomena that we think are physically more fundamental than others. For example, you might imagine that a fluid like water is made up of molecules, and these molecules are all moving around. These molecules have various properties. They interact with themselves and with other forms of matter in various ways. When you have enough of these molecules, and if we're talking about water molecules in particular, H2O, we have this experience that water can be wet, that we can have water, on our clothes or in our hair, and our hair will be wet. I think at some level, when you study science, you recognize that these things like wetness are what we call emergent properties. Emergent means that they arise at kind of a high level. They arise when you've got lots and lots of moving parts, and you kind of zoom out and you coarse grain over your picture of what's going on, and you have these sort of gross properties like wetness. And I think a lot of us, at this point, we recognize that wetness is not something to be found at the level of an individual water molecule. It's an emergent feature. Temperature is another very good example. We have this experience of temperature. We know what it feels like to feel hot or cold, to touch an object and feel that it is hot or cold. Hotness and coldness for ordinary kinds of objects is an emergent feature. It emerges from the motions of all the tiny constituent elements of that object. If you zoom way in at a very fine-grained level and look at what all the little individual elements are doing, you'll see they're all jittering around in various ways. And you'll see that things at higher temperature correspond roughly to those little elements vibrating or moving around or oscillating around more quickly, more rapidly. We have this sense that rapid motion is more fundamental. Temperature is this sort of macro meaning big scale phenomenon that we experience. And I think we understand that things like temperature, just like things like color, these are things that may not be as fundamental as the behaviors of the fundamental constituents that make up the objects that exhibit these features. So if we take the behaviors of these constituent elements to be really happening, we are realists, at least with respect to those features. But these higher level macro properties, maybe we're a little bit less than realist about those. Does this mean that we are realists full stop, or that we're realists about some things and not others? I think we can be realists about some things and maybe not about others. But actually, this is an interesting point, because you could also ask, merely because things like temperature or color don't seem to make sense at the level of individual constituent particles, just because they're emergent properties, does that mean that they're not real? Does something have to be fundamental to be real? I don't know the answer to that question. I think chairs are real even though they're not fundamental. You're not going to find chairs written down in the fundamental laws of physics. I'm willing to say that things that arise emergently can be real, but maybe they're real in a less fundamental way than other things. So I don't know if this is a good answer to the question about whether you're a full-blown realist about everything or only about some things. I think maybe a more precise way to say it is, maybe we can take some things to be more fundamentally real than others, and other things to be higher level or more emergent than others. And so it's a question of degree. The orthodox position about quantum theory is, according to David Griffiths' book, the statement that all the features of quantum systems we can measure, all the properties of quantum mechanical particles, arise through the process of measuring them, and don't have pre-existing values that we are merely passively revealing as we observe them. That's, he calls it the orthodox view. And then there's the agnostic view, which is, as you said, right, it's the view that we either can't make a distinction between these things, or we're just not going to try to make a distinction between these things, or it doesn't matter. There are various interpretive approaches to thinking about quantum theory. I don't know that they neatly fall into that trichotomy. In David Griffiths' book, he has various footnotes in this part of the book. I think it's section 1.2, in which he acknowledges that there are frameworks and interpretations that don't quite fit into this scheme that he set up. But for the purposes of pedagogy, for the purposes of teaching quantum mechanics, these nuances aren't so important. He talks about them at somewhat greater length in the afterword at the last chapter of his book. I think it's chapter 12. I'm a very big fan of Griffiths. He's a very inspiring figure to me. I love a lot of what he's worked on, but I think one needs to be really careful when introducing students to quantum mechanics to get them on the right foot, to avoid saying things that even you, the author, are aware steamroll over very important nuances. It's true that we can't try to tell newcomers to a subject absolutely everything in full detail about a subject. We can't be completely, totally honest just because there's too much to say, because it would be overwhelming, because it would be difficult for students to find a place to grab a hold of the subject and find an on-ramp into it. But I do think we have to be very careful not to mislead. So that's what I'll say about that trichotomy. My view is that some level of realism is necessary, at least in like the broad sense of realism. There are a lot of different kinds of realism. There's naive scientific realism, which is just the idea that if you have a scientific theory, then you're supposed to take the ingredients of that theory and regard them as true, real aspects of reality.
Yep.
There have been arguments over the years that naive scientific realism is not a reliable posture to take toward metaphysics, toward the real world, because periodically we overthrow our scientific theories. If you take too seriously the ingredients of any given scientific theory, what do you do when the theory is replaced with something else? And if you think that all of our scientific theories are just waiting to be replaced by something else in a never-ending succession of scientific development, then you might be very cautious or even skeptical that we should ever try to take the ingredients of our current best scientific theories seriously as painting a picture of what the real world really looks like. This pessimistic attitude is called pessimistic meta-induction. Just the idea that because in the past, all of our scientific theories have turned out to be either incomplete or mistaken, that we can, induction is the idea of taking from the past and projecting into the future, the idea that this will continue to be the case, and therefore we have to be very careful about taking the ingredients of our scientific theories too seriously. I think pessimistic meta-induction is too pessimistic. Because although we do develop better scientific theories, what we often find is that yes, the ingredients of our previous most successful scientific theory are no longer taken to be fundamental. What we often find is that in the new scientific theory, they continue to exist, but as emergent or higher level or approximate features of the next theory. So they exist, at least in some cases, in the optimal cases, as much as chairs exist. Mm-hmm. If you thought that the world was described by fundamental chairs, and then you discover that in fact there are atoms and chairs are made of atoms, that doesn't mean that chairs don't exist anymore. And it doesn't mean that you were wrong to take seriously chairs as parts of your picture of physical reality. So pessimistic meta-induction may not be quite as problematic as maybe people think it could be. Of course, there are examples where we really did throw out things altogether. The ether theory, for example, the luminiferous ether theory. This was the idea that if light is a wave and waves should be waves of some material oscillating around, then what was the material that's oscillating when a light wave propagates through space? And this material, which was supposed to suffuse all of three-dimensional space, was called the luminiferous ether. Luminiferous, literally light-bearing, and ether meaning heavenly substance. When Einstein came along in 1905 with his special theory of relativity, the ether was banished. It was eliminated. It turned out not to be, at least according to special relativity, or at least according to the theories that we have now, to be a fundamental feature of reality or an emergent feature of reality. It turned out to just be not a part of reality at all. So what does this mean? It means that some of the ingredients of our current best physical theories may be totally overthrown. Other ingredients may persist at an approximate or emergent level, and in the later theory become things that arise at a higher level from the more fundamental constituents of the later theory. Or maybe we're correct. We've found something that really is a part of reality and it will persist. We can't know. I guess that's the biggest lesson of science, right? Is that you can't ever truly know anything. Everything we think we can know is shaded in varying degrees of epistemic, meaning knowledge or belief-related uncertainty. Everything is shaded in varying levels of epistemic uncertainty. We are limited beings. We don't have the right to demand that we know exactly what's going on. We're just trying to do our best. But I do think that some level of realism is important. If you deny that anything at all is real, going beyond scientific realism and just declaring that nothing is real, this becomes a self-undermining thesis. That means a claim about reality that undoes itself. Because if nothing is real, then apparently we're not real. And if we're not real, then who's doing the questioning about what's real? You run right into these old thought experiments that go back to Descartes. Descartes says, I think, therefore I am. That means there's something real.
Yeah.
And if you deny that everything is real, then the whole process sort of comes undone. How can we trust our scientific theories to begin with, which are based on empirical, meaning experimental, observational investigation, if our experiments and observations themselves fail to be real? The whole thing just sort of comes undone. I think this happens anytime you try to advocate for a totalizing metaphysical thesis. Anytime you try to argue that there is some one universal, absolute theory about how everything is supposed to work, you often run into circles. You find that it in some way undermines itself. So I can't be a full-blown anti-realist, although I think that maybe some things are more real than others. There's a book that I read that I don't know if any of your listeners have read this book. It's called Solaris by Stanislav Lem. Yeah. And I don't want to give away the story. People should read it. But there's a scene in which the protagonist, who's a scientist aboard this research vessel on a very strange planet very, very, very far away from the solar system, is investigating some material under a very, very powerful microscope, a microscope of the future, and is looking at this material and sees that it appears to be made of molecules, atoms, and somehow this microscope can see into atoms, which, okay, just suspend your disbelief a little bit, but this just ordinary microscope can see inside of atoms, down below atoms, can see the fundamental constituents of the atoms. And as this microscope, continues to zoom in closer and closer, eventually it arrives at nothing.
Right.
There's a void. There's emptiness. There's nothing where there should be something. At the bottom of this material, at its finest level, there is void only. There is nothing. And I when I read the book, I reread that part of the book several times. It left an imprint on me because the prospect that at the bottom of reality is just void, is nothing, I find emotionally terrifying. And maybe that's irrational. Maybe one should have more rational reasons to believe that one should be a realist about things. But just at an emotional level, I really, really want there to be something down there. But I'll say, just as an intellectual proposition, even if you don't have an emotional attachment to the idea of realism, it's still, I think, an important intellectual exercise. Can we find a way to think about the world? Can we find a way to formulate our scientific theories so that realism can survive? Maybe the answer will be no. But if we can, I think it's worthwhile to see if that's possible. There's a poem by Archibald MacLeish called The End of the World. I don't know if viewers have heard this poem before. The poem is about a circus performance And there are all of these circus acts, and there are acrobats and lions all dancing around and putting on a show. And then suddenly the roof of the circus tent flies off. And all the people inside look up at the sky, into the void. They look into, and the poem ends, they look at nothing, 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 nothing at all. And that's how it ends. It's called the end of the world. And for me, again, it's just an emotional response to wanting there to be something rather than just complete nothing at the bottom of reality. I like good poetry because sometimes it captures a certain kind of emotional feeling that can be difficult to put into words.
Let me try to convince you on the anti-realist position. But before I go there, firstly, I'm just happy you've committed to a position, this hybrid realism, because David Griffiths in that same book, and you alluded to this, he was quite dismissive of the entire question. He said it is no wonder that generations of physicists retreated to the agnostic position and advised the students not to waste time worrying about the conceptual foundations of the theory. It's quite rare to find a textbook passing judgment on a theory and saying it's a waste of time. I thought that was quite interesting. So I'm happy that you have committed to a position. I'm going to try and convince you towards anti-realism with an incident from your own childhood. When you were around 5 years old, I think you were at high school in an assembly room. The teacher was talking. There was a piano in front of you.
I think I was in elementary school.
Elementary school. Okay. Elementary school. American schooling system is...
I don't want people to think as a 5-year-old I was in high school, but it's okay.
When you were in elementary school and you were sitting in this room, it was an assembly room, the teacher was talking, there's a piano in front of you, and the feet of the piano look like lion's paws. And that moment is quite a special one in your life because for some reason, you just became aware of your existence. Before I try to convince you, why don't you describe it? What was that moment like? What did you feel in that moment?
I think you've described it perfectly well. I became aware of my existence. I became fascinated by it, and I attempted to communicate my feelings to one of the other students sitting next to me and was unsuccessful.
Yeah, that incident sparked this love for the philosophy of mind for you. I'm curious to hear why that experience didn't sway you towards the anti-realist position, that everything you see around you, this reality in double quotes, is nothing but a filtered version of whatever objective reality is, filtered through this overlay of your awareness, your existence, your consciousness. And when you spoke about not knowing where to draw that cut of what's fundamental and what's emergent, it feels like every single thing I see around me is emergent from this overlay of consciousness. So why would you not take the anti-realist position then?
I mean, I suppose one could go all the way to full-blown idealism, philosophical idealism, that all there is mind. I don't have a particularly sophisticated response to this, except that when we poke reality, it seems to poke back at us. So one of the strongest challenges to realism comes from quantum mechanics. Quantum mechanics, the way that it's usually formulated, sets up a number of potential challenges to how we try to think about realism. Griffiths, in his textbook, talks about some of these challenges to our picture of realism. Nonetheless, when we measure a property of a system, call it property A, and we measure property A again, we measure property A again, we can often set situations up in which we get robust, reliable, consistent results as we keep remeasuring property A. This already gives me a feeling like we're probing something that is out there and not merely something that comes out of our minds. But for quantum systems, all quantum systems feature a property called contextuality, which is closely related to this notion that there can be incompatible observable features of systems. Mm-hmm. This is a characteristic that all quantum systems, no matter how simple, share. Even a quantum system consisting of a single particle, a single structureless spin zero particle that can't be entangled with anything because all you have is just that one particle alone, you'd still have this notion of incompatible measurable quantities. Let's suppose that we call one of these incompatible quantities B. We go out and we measure B this feature or observable feature B of our particle. We get a result, and then we immediately go back and try to measure A again. What we'll find is that the result for A may have changed. This is a consistent finding. It's what it means at some operational, meaning in practice, level when we examine incompatible observables. We say that the incompatible observables belong to different contexts, different measurement contexts. The fact that measuring B can lead to a change in what we'll then get for measurements of A strikes me as evidence that the measurement of B did something to the world outside of our heads. Now, this could be mistaken. Ultimately, there is no way to know for sure whether our experience of the world around us is truly there or is simply generated by our conscious experience.
The act of you measuring it might have changed the value itself.
That's right. So I'll just retreat to my emotional position. When I look upon my loved ones, of whom I am blessed to have many, it matters to me emotionally that they're really there. I can't know for certain whether they're really there. There's some things as epistemically limited beings that we can't ever know with absolute certainty. But if we can find a description of nature, a scientific description of nature that is at least consistent with their existence out in the world, separate from my consciousness, I would like to see if we can find that scientific description. If we can't, if we can show in some provable way that there is no internally consistent, empirically adequate meaning agrees with experimental observation, makes the right predictions. If we cannot find a self-consistent, empirically adequate scientific description that is compatible with the existence of an external reality outside of our minds, that would be a very interesting thing. I don't think we've adequately probed that question, and it's one reason why I continue to work on it as someone who works at the intersection of philosophy and physics.
Before we dive into that work you've done, I want to properly set the context and also define the problem statement. You've alluded to this thing called quantum mechanics, quantum physics multiple times. I do want to define it. I believe one of the courses you teach at Harvard is Physics 19, Introduction to Theoretical Physics. So I'm hoping this is going to be an easy exercise for you. Let's assume I'm a 12-year-old. Also an easy exercise for you, I'm sure. Not a stretch of imagination. Intellectually, I'm stuck at that age. What is textbook quantum theory? What is quantum mechanics? Please explain it to me as if I'm 12.
Explaining quantum mechanics to a 12-year-old. Interesting question. We look around at the world and we see things. We see people. We see objects. We see phenomena. We see movement. We see behavior. We see patterns. We see patterns all around us. When you see patterns and those patterns are consistent, you see them over and over again, eventually you learn that you can make predictions about things you'll see. You drop an object, the object falls. You drop the object again, it falls in much the same way. You notice there's a pattern. When you observe enough patterns, you start developing ways of talking about those patterns. First, you talk about those patterns in whatever your native language is. But as the patterns get more complicated, we find the need to develop more precise ways of talking about those patterns, of describing them, of telling other people about them, of using those patterns to predict what's going to come next. The precise language that we use for describing those patterns, for explaining, for arguing about, for sharing, for talking about those patterns is called mathematics. Now, mathematics is many things. I don't want to say that the only thing we use mathematics for is for science, but it's one particular thing that mathematics appears to be really good for, and in many ways designed for. We have crafted mathematics, at least in part, to allow us to talk about the patterns in the world that we see around us. when we come up with a nice mathematical way to talk about a pattern, we call that a law of physics. We call it a rule of physics, a rule of the universe. There is a sense in which what we're trying to do in physics is figure out those rules of the universe, find mathematical expression for the patterns that we seem to see around us all the time.
Okay.
There are debates right now, especially among certain segments in the philosophical community, over what those patterns really are. Are those patterns things that are simply happening for reasons that don't have a deeper explanation, and we introduce this mathematical language just to summarize the patterns that we're seeing, just for convenience? Or is the fact that we see patterns around us telling us that there really are, in some very deep sense, laws that govern the universe, laws that make those patterns come about in a particular way? I don't have an answer to that question, 12-year-old. I don't have an answer. But this is a debate that's raging among philosophers, those who argue that our mathematical laws merely summarize in as best, as optimal a way as possible, have come to be known as the Humeans. This is a term, it's named after David Hume, a philosopher who had a lot to say about the nature of reality centuries ago. The view that the laws of nature are freestanding things just out there in the world that compel phenomena in the universe to behave according to these patterns. That view goes by various names. I like to call it primitivism, the idea that that laws are a primitive, basic feature of reality. This is known as the governing paradigm, the idea that the laws exist outside of reality in some sense and act on reality to bring about the phenomena, like governing them, making them behave in a certain way. Now, there's a long-running debate over, between the two camps here. The Humeans will say, what does it mean to say that a law of nature exists outside of reality and reaches in? Where does it exist? How does it reach in? How does it make reality obey it? And the primitivists will come back and will say, well, if there aren't laws, are you just saying that these patterns happen for no reason? And if they happen for no reason, then there's no explanation at all. And rather than posit a few laws of physics, you have to posit all the phenomena. That just seems like way more, we call them brute facts, way more things that you're just declaring are out there in the world. And so this debate's been going on a very long time.
Right.
Some of those mathematical rules allow us to say that if we know enough about how things start, then we can predict with certainty where they will go, how they will change, in what way they will end up. Rules of this form, roughly speaking, are called deterministic. If you're given the starting conditions and you're given these rules, then together, those initial conditions and those dynamical laws, dynamical law means laws that summarize or govern the way things change. Those initial conditions, those dynamical laws determine how things will go, how things will end up. They'll determine them completely. That's determinism. There are other kinds of laws that don't tell us exactly what's going to happen, even if we know as best we can the starting conditions, the initial conditions. What I would say to this 12-year-old is imagine you're playing a game of dice or throwing coins. 12-year-olds mostly know that when you throw a coin, if it's a fair coin, there'll be a 50-50 chance it will land heads or tails. So we would say that if you're trying to describe the coin and its behavior using the language of mathematics, we would not assign a rule that tells us exactly how the coin is going to land. We may not have such a rule, even if we know how the coin started. There is, of course, an argument that if we know exactly how the coin started with incredible precision and we know all the details about how it's thrown, then maybe we could make a deterministic prediction. But in practice, we often don't have that level of description. And so we don't make a prediction about exactly how the coin will land. We'll say the coin has a 50-50 chance of landing this way or that. So some of our scientific theories will maybe involve deterministic kinds of laws, and some of our scientific theories will have laws that talk in terms of probability, chances, probability, the chance that something will happen a certain way or another way. The laws that we got from Isaac Newton, roughly speaking, are of the deterministic kind. If you know that you've got a collection of bodies, of objects in space, and you have details about what condition they're in at the beginning of your experiment, the beginning of your observations, if you have the right kind of information, then you can predict using Newton's dynamical laws of motion, Newton's 3 laws of motion, how this object will evolve or change with time in more or less deterministic way. Now, in practice, this is often not possible. It may be that the behavior of the system depends very, very, very sensitively on those initial conditions, like with a coin, and that we can't make determinative predictions, that we may be stuck using probabilities. Systems in Newtonian mechanics whose behavior depends very, very, very sensitively on the initial conditions, in the sense that tiny changes to the initial conditions that may be too tiny for us to notice can lead to drastic changes in the later behavior. These systems are called chaotic. The study of these systems is called the study of chaos.
Chaos theory.
Chaos theory, right.
Yeah.
So even in the Newtonian case, we may find ourselves having to give up our ability to treat the laws as fully deterministic just as a matter of practice.
Mm-hmm.
And there have been other physical theories since Newton's laws. There's physical theories that describe how electric fields change with time and how they interact with objects, and theories that describe how magnetic fields change with time and how they interact with material objects. And a lot of development has gone into the development of all these theories over the years. In 1900, Max Planck introduced his quantum hypothesis in order to account for certain patterns of observations that were being made about objects that are heated. Heated objects emit light of various colors according to a very particular kind of a pattern. Max Planck was able to account for this pattern, find a mathematical description of it, a precise mathematical description of it, by imagining that you could only trigger or excite different colors in discrete amounts, in steps, not smoothly, for these objects. And this became known as his quantum hypothesis.
Mm-hmm.
Over the years that followed, people developed a mathematical theory of microscopic objects, very small things, microscopic theory of molecules and atoms, and eventually subatomic particles, things smaller than atoms, things that you 12-year-old might have heard of, electrons and protons and neutrons that make up atoms. It took a long time to develop this theory. From 1900 to 1925, people relied on a variety of partial mathematical descriptions. This was the era that later became known as the old quantum theory. Formulas that sort of worked but didn't quite work. Formulas that didn't quite fit together into a comprehensive set of equations. That didn't fit together into a mathematical framework that was unified, that fit together like a jigsaw puzzle fits together. I could go deeper into the history. I've gone deeper into the history in other conversations. Let me not do that here. People are welcome to go look up, the history themselves or listen to, the descriptions I've given of the history elsewhere. But let me just say to this 12-year-old, the theory that developed starting in 1925 and reached its culmination in the early 1930s with the work of people like Paul Dirac and John von Neumann, with a tremendous amount of work by others like Wolfgang Pauli and Louis de Broglie and Erwin Schrödinger and Werner Heisenberg. The theory that developed has the following structure. We start with some basic ground rules or assumptions, the starting points the postulates, the axioms. You can use different words for these things. These are the raw mathematical starting ingredients out of which we're going to build the theory. Much like we build Newton's theory of motion out of his idea that we have material bodies in space, obeying his famous 3 laws of motion. What are these axioms? What are these postulates or premises? The first is that we will not talk about bodies in space. Instead, we will assign a system being some physical thing that we want to study and make predictions about. We call that a system. We will assign it a mathematical thing, and this mathematical thing is called a quantum state. Now, 12-year-old probably doesn't maybe know very much about Hilbert spaces, so I'm going to avoid using that language here. I'm just going to say that we have this mathematical thing called a quantum state.
Right.
It has some basic rules, some basic mathematical properties and rules, but these rules are all purely mathematical. There's statements about how this mathematical thing is supposed to, what mathematical features, what kinds of mathematical operations you can do with it.
For the 18-year-old listening in, what is a Hilbert space? A very quick definition.
Sure. So a Hilbert space is a vector space. A vector space means a collection of mathematical things that can be added together to get new things still in that set or space and multiplied by certain kinds of numbers called complex numbers.
Mm-hmm.
And there are some basic ground rules that this vector space is supposed to have. The rule for adding vectors together is supposed to be commutative. It's supposed to be associative. Multiplication by numbers is supposed to be commutative and associative and distributive. There's supposed to be a zero vector that does nothing. Every vector is supposed to have another vector that when you add them together, you get the zero vector. There's some basic arithmetic ground rules. This makes a vector space. To be a Hilbert space, you need a little more. You need a rule that lets you take 2 vectors, 2 elements of this vector space, and combine them to get a complex number. And this rule for combining them is called a dot product or inner product. And this inner product is supposed to have certain mathematical features consistent with the structure of this being a part of a Hilbert space. So it's got to have certain properties when you, for example, interchange the 2 vectors. If you take the 2 vectors and reverse them, you're supposed to get the complex conjugate of what you had before. This inner product is supposed to have a property called positive definiteness. It has to have the right kind of distributivity property called sesquilinearity. It's supposed to have a number of properties. And this Hilbert space is not supposed to have any holes in it. Holes, like HOLES. There should be no gaps in it. If you have a collection of vectors that you can arrange in like a line, imagine mentally you have a sequence or list of vectors in your head, and the vectors appear to be getting closer and closer to approximating some vector. And you could imagine this list going on forever and getting ever closer to some vector. If that ever happens, we say we have what's called a Cauchy sequence. And the end result of that Cauchy sequence is supposed to still be a vector in this vector space. Then we say that this is a so-called complete vector space. And a Hilbert space is a complete inner product vector space over the complex numbers. Hilbert spaces have some dimension. The dimension of a Hilbert space is essentially how many different vectors you can have that you can't make out of each other. So a 3-dimensional vector space is one where, like in 3D space, you have 3 vectors you can draw 3 arrows, and it's easy to come up with 3 arrows where you cannot make any one of the arrows out of the other 2.
Mm-hmm.
Any 2 arrows will define a plane, and then any vector that is not in that plane cannot be made out of those 2 arrows. So this the maximum number of such vectors that are different from each other and cannot be constructed out of each other by adding them together, we call this the dimension of the vector space. Since the Hilbert space has some dimension. Okay, so we'll bracket that off. That's yeah, and so quantum state is some object that lives in or on this Hilbert space. It could be a vector in this Hilbert space, but more generally, it's what's called an operator, a density operator on the Hilbert space.
Got it.
This gets very technical, so I'll just move that aside.
Back to the 12-year-old.
There is this thing called a quantum state. It's a mathematical thing that we use to describe this quantum system. This mathematical thing, when not disturbed, when left to itself,
not measured.
Certainly not measured.
Not measured.
Not measured.
Is that what you mean by not disturbed?
Not necessarily. Measurement is one kind of disturbance.
Okay.
There are other kinds of disturbances. If our system, the system that we're trying to describe with this quantum state, is left to do its own thing, it's not interacting with, it's not talking to, it's not exchanging things with any other systems, then it changes according to a rule. And this rule has kind of a funny name. It's called unitary time evolution. This can often be boiled down to a very famous equation that appears on the very first page of David Griffiths' textbook called the Schrödinger equation. So there's an equation that tells us how this thing changes, this mathematical thing changes when the system is not being disturbed. But so far, all the things I've said have been purely about mathematics. We have a mathematical thing called a quantum state, and it changes according to this mathematical rule called unitary time evolution. How do we connect this up to the patterns that we see in nature around us, to our observations? That is, how do we get the empirical content out of this picture? Empirical just means the things that we experimentally observe or see. Those come from some additional assumptions, some additional premises or axioms. These are called the measurement axioms. The measurement axioms say that if an observer, one who observes, like a person, let's say, but maybe not necessarily a person, but maybe not necessarily a person. This is a bit mysterious. But when an observer of some kind measures some property of a system described by some quantum state, there is another kind of mathematical thing. This other kind of mathematical thing is called an operator. And the mathematical features of this operator, when studied, allow you to predict what you could get when you read the results of your measurement. The things you can get are called eigenvalues. They're called the eigenvalues of that operator. The word eigenvalue apparently came from David Hilbert, the great mathematician from the end of the 19th and into the 20th century. He was at Göttingen. So the eigenvalues are a list of features of this mathematical operator. And by studying this mathematical operator and by figuring out what these numbers, these eigenvalues are, they're real numbers, you can predict what are the possible things you could find when you measure that property of the system. That's a prediction about what you'll see in nature. That's a prediction about a pattern. When you measure this property of this kind of system, you'll always see one of these specific numbers, one of these eigenvalues. So we're already connecting with patterns of things we see. There's a pattern. We see certain kinds of things and not other kinds of things. When we measure this feature, this observable property of this kind of a system, that's a pattern. And now we're beginning to see an axiom that tells us about those patterns that we see. The next measurement axiom tells us what are the chances that we'll see one of those numbers, or one of the other numbers, or one of the other numbers. It's an axiom that tells us what the probabilities are going to be of our measurement outcomes. There's a precise mathematical formula that takes the mathematical quantum state from our first axiom and takes the operator from the axiom I just mentioned and combines them together in just the right way. And this formula is called the Born rule. It's named after Max Born, one of the people who developed quantum theory. And we get a prediction for the probability that we'll get that particular outcome. This Born rule axiom lets us make predictions about measurement outcome probabilities. Mm-hmm. It allows us to assign a probability, a number, a different kind of a number, not the number of the thing we're measuring, but a number that tells us what are the chances we'll see that particular number of the thing we measure. Just like with a coin, we can say that for a fair coin, there's a 50-50 chance. The Born rule says that for different properties we could measure, there's certain probabilities that we'll see particular results. The final assumption or axiom that leads to quantum theory says that after you've done your measurement and obtained a particular numerical outcome, one of the eigenvalues, you're supposed to change the system's quantum state in a very particular way. You're supposed to simplify it or reduce it or collapse it in such a way that were you to do the same exact measurement again of the same observable feature, then with essentially perfect 100% chance, you would get exactly the same answer you found in the previous measurement. This is known as the collapse postulate or the collapse axiom. And those are the axioms of quantum theory. Those are the axioms that you'll find when you read deeply enough into any good textbook on quantum theory. That includes David Griffiths' book. These are the agreed upon axioms, and they're known as the Dirac from Paul Dirac, von Neumann from John von Neumann, the Dirac-von Neumann axioms. And this is the part that people mostly agree on. Mostly. At least people agree that if you're talking about textbook quantum mechanics, textbook quantum theory, then these are the axioms you're taking to be your starting mathematical ingredients. I should say that I sometimes say quantum theory and sometimes quantum mechanics. Sometimes people use the word quantum theory to mean the general theory, quantum of anything, and quantum mechanics specifically when quantum theory is applied to systems of particles in particular. But there do appear to be other kinds of things in the world like fields, like the electric field, the magnetic field, the gravitational field, or systems in computers made of memory registers, bits inside of a computer memory. Maybe those are ultimately made of particles, but when we describe them with quantum theory, we're not using the usual quantum mechanics of particles. So some people use the word quantum mechanics specifically when the kind of system we're trying to study is explicitly made of particles. Although sometimes people use the word quantum mechanics more broadly for the overall theory. So those are the axioms. Now here's what I would tell the 12-year-old. Maybe you've watched a science documentary, or maybe you've been in school and read in one of your books, or maybe you've read a science fiction book, or maybe you've listened on the radio to a program where people were talking about quantum theory. And maybe you've heard them say things like, quantum theory tells us that an atom can be in two places at once. Quantum theory tells us that when a particle goes from point A to point B, it takes every single path from point A to point B to get there. Maybe you've heard, maybe in a elementary or middle school chemistry class, that an atom is not empty, but it's really filled with a cloud. An electron is kind of a cloud made of what's called a wave function, and this wave function fills the atom. Maybe you've heard that a cat can be alive and dead. Maybe you've heard that quantum theory tells us that everything that can physically happen does happen in some giant branching quantum multiverse. But maybe you've heard even simpler things. Maybe you've heard that electrons can move around and every once in a while they spit out a photon. Or maybe you've heard that when an electron meets an anti-electron, a positron, why is it that electron antiparticles get a name, positron, but others don't? Anti-electrons get a name called positrons, but electrons, it's funny. But when an electron meets its antiparticle, they can annihilate and become a photon. So you imagine this picture where an electron is moving in one way and a positron is moving another way, and they come together and a photon comes out. But if you look at the axioms that I listed, the Dirac-von Neumann axioms, quantum states, unitary evolution of these quantum states, all pure mathematical, and then these measurement axioms, you could measure something and you'll get an eigenvalue of a certain kind of mathematical operator with a probability given by the Born rule, and the quantum state is supposed to change, collapse. The axioms say nothing about any of those things. The axioms do not say that a system can be in two places at once. The axioms do not say that systems take every path from point A to point B. The axioms don't say that an atom is filled with wave function. The axioms don't say that a cat is alive and dead or can be alive and dead at the same time. The axioms don't say that every possible physical thing happens in some sprawling, vast quantum multiverse, branching and branching from every point in time. The axioms don't say that electrons can just emit a photon, or that an electron and a positron, they meet, they find each other, they meet, and a photon comes out. The axioms don't say any of that. The axioms talk about these abstract quantum states changing, and then the axioms tell us what happens when we do measurements, and that's it. That's striking, isn't it? And very different from the axiomatic formulations of our other physical theories. Let's go back to Newtonian mechanics again, Newton's picture of the world. There are bodies moving around in space. I didn't say what Newton's laws were, but the laws talk about different frames of motion you can make observations in, and how in those different frames of motion objects will behave. They'll follow straight lines at constant speed unless they interact with each other through forces. And if you know what the forces are, you can predict how the bodies will change in motion, how their motion will change. Yeah. This gives a very physical picture of what's going on in the world around us, and in particular, a picture that doesn't rely on somewhat mysterious ingredients like observers or agents doing mysterious things like measurements. When you look at how we formulate our other physical theories like electricity and magnetism, or Einstein's theory of general relativity, you get much more mathematically complicated theories. But you still get theories that paint pictures of phenomena happening in the world, whether we as observers or agents are there or not, that describe things changing and doing things, following paths, exhibiting behavior. These are theories in which phenomena happen in a very broad sense. There's this category consisting of phenomena taking place, and these theories say that those phenomena, at least at their level of scientific description, really are happening. These are phenomena happening theories. But the axioms of quantum theory don't seem to be like that. They don't talk about phenomena happening. To the extent that they make a connection to reality, to empirical reality, it is only through the very narrow category of measurements, apparently done by observers or agents. This is not satisfying. This is troubling. But that doesn't mean it's wrong. I mean, no one ever promised us a rose garden. Maybe nature just isn't forthcoming with happening of phenomena in what is presumably our most important fundamental scientific theory, quantum theory. Maybe that's just the way things are. However, as an intellectual exercise, I think it's worthwhile to see if we can reformulate quantum theory as a theory of phenomena truly happening. And even more, the fact that people tell these stories about quantum theory, things being in two places at once or following all these paths, or that electrons really are moving around and emitting particles and so forth, the fact that people tell these stories means at some level people really do still think this way. It would be nice for this to be honest. It would be nice to be able to tell someone who's studying early universe cosmology that when they talk about what gases were doing in the early universe, they're not just telling a colorful tale, but they're describing something that really happened, phenomena that really happened, even though there was no one there looking at it as it was happening. It would make us more honest to be able to transcend this narrow category of measurement phenomena alone and be able to talk about this much broader category of phenomena happening. That is, it would be nice if we could transcend this category problem in quantum theory.
So that's standard quantum theory. That's also define the problem statement. You've already alluded to the problems with the measurement axioms. In the paper, Remarks on the Mind-Body Question, Eugene Wigner put forward the Wigner's friend thought experiment, which highlighted, or at least visualized for people like me, some of the gaping holes with these measurement axioms. So what is the Wigner's friend thought experiment? And then how does that elucidate the measurement problem?
The Wigner's friend thought experiment, again, and I have mentioned this before in previous conversations, goes back at least to Hugh Everett's long-form PhD thesis. But again, Wigner and Everett were probably talking at the time. It's very simple to state. There's two observers. One is inside a box that is sufficiently sealed for the duration of the experiment that we can treat it as a perfectly sealed box. Inside the box, there is an observer called Wigner's friend with some quantum system that Wigner's friend is measuring. And outside the box is Wigner. So an observer in, an observer out. Wigner's friend does what is presumably a measurement process on the quantum system. And the question is, do we invoke the measurement axioms or not? And the way I like to think about the Wigner's friend thought experiment is in terms of a flowchart. And I'm happy to send you a copy of this flowchart. But Wigner's friend makes you, it forces you to make some decision about what you want to do. Wigner on the outside describes this system with a quantum state evolving in some way. Question 1, does the quantum state collapse or not? If yes, then we have another question. Does it collapse because of Wigner's friend's measurement? If yes, then we run into the measurement problem, the category problem, all the problems we talked about. Why does that thing count as a measurement? What if Wigner's friend were smaller? What if Wigner's friend were a tardigrade or a bacterium or a buckyball? Like, at what point is it a measurement? What point is not a measurement? We run head first into the measurement problem as well as the other problems. If you say no to that question, so yes to the quantum state collapsing, but no to Wigner's friend having been responsible for it, then there's some other mechanism that causes collapse, and this leads you into the dynamical collapse approaches to quantum theory. Now suppose instead of saying yes, it collapses, we say no, it does not collapse. This, by the way, will have different experimental signatures in principle, because if it has not collapsed, then in principle there are interference experiments you could do with the entire box that you wouldn't have been able to do if it truly collapsed. So there's actually like a practical difference here. And whether you say yes or no to this question is the ambiguity in the Dirac-von Neumann axioms with a clear, although maybe very difficult in practice, to measure consequence. But the Dirac-von Neumann axioms don't say whether you're supposed to say yes or no to that first question. You have to just choose, and there's the ambiguity. We already covered what happens if you say it does collapse. Now let's suppose you say it does not collapse. If it doesn't collapse, your next question is, despite it not collapsing, did Wigner's friend get a unique answer? Is there hidden under this wave function an actual answer that Wigner's friend knows? If you say yes, then by definition, we call that a hidden variable. By definition, we're saying that the quantum state that Wigner would have assigned is incomplete.
Mm-hmm.
That's maybe the better way to say it. It's an incomplete quantum state. Or in a picture like the one I've presented, this indivisible stochastic approach, there just isn't a quantum state at a fundamental level. There are only these ways things really are. But in any event, the wave function, whether it exists or not, is simply not complete. The quantum state is not complete. And this leads you to pilot wave theories or a theory like mine, or the modal interpretations, or various perspectival interpretations, or a lot of people who working in physics implicitly take this view but don't want to call it hidden variables. They want the overall quantum state not to collapse, but they also want there to be a fact of the matter about the result. If you do that, you are committing to some kind of hidden variables type approach, some incomplete wave function approach. If you do not say that there was in fact a definite result, well, then your next question is, were there many results or no results? If you say many results, then you have something like an Everettian many worlds picture with all of the usual problems of how to make sense of probability and the stone soup problem and all the various problems we've talked about. And if you say that there was no answer, then you run into an anti-realism loop. Well, if that result wasn't real, then are any results by anyone ever real, including Wigner or anybody? Because we could be Wigner's friend, maybe we are Wigner's friend, and if no one's ever actually getting any results, then the whole process is entirely self-undermining. I think this flowchart is really helpful in thinking about this problem. I mean, of course, one other option is that quantum theory is just totally wrong. That may also be true. That's an option. So I guess maybe before all of this is the question, do you believe quantum theory is correctly maybe that's the question.
Should have started with that.
Should have started with that. But if you're going to take quantum theory seriously, as I think many of us do because it works so well, then you have to take a stand somewhere in this picture. And you can't just say, I refuse to take a stand, because it's a flowchart with yes or no questions, right? I think the honest thing is to face up to this. So I think this gives a really clear picture, and I am very explicitly taking the point of view that the state vector, the quantum state, is not the full story. And in my case, I'm saying it's not physical at all. It's merely a mathematical artifact. It's what I call it's a what's the word I use for this? It's an appurtenance. It's an appurtenance of quantum theory. It's a mathematical appurtenance. It's like a Hamilton-Jacobi function or a Lagrangian. It's not like a physical object. And what's physical is the actual configuration of the system in question. Now, when we've encountered ambiguities or breakdowns in our other physical theories, and all of our other physical theories do have places where they break down. When the mathematics of a given physical theory breaks down, we call it a singularity in the theory. I know there's this popular idea that singularities are like point-like things in the middle of black holes, but the notion of a singularity is a much more general idea. It's just any situation in which the mathematical laws of your theory stop working or stop making predictions or become ambiguous or whatever. And in all of our theories, we have them. I mean, I just mentioned, singularities in general relativity. The general relativity seems to break down at certain places in space-time, maybe when black holes form or the beginning of the universe. And people look at those singularities as things worthy of study. People face up to them and recognize them as things worth thinking about, taking seriously. It's very strange that the ambiguities in quantum theory are not seen in the same way. They're not seen as things that we should study and understand and maybe improve. For rather complicated historical reasons, the view was instead that if you're thinking about them or taking them seriously, you're simply not thinking in a sophisticated enough or mature enough way about quantum theory. The idea is that quantum theory has taught us to see the world differently, to see the world in a way where we no longer worry about those ambiguities. And if you're worried about them, it means that you are immature. This view has been codified by many people. I think the most striking place I've ever seen it codified is in an essay from 1958 by Freeman Dyson. Freeman Dyson wrote an essay. I don't know if you link to essays, but I can certainly give you a link to this essay.
Definitely.
And he says that when students first encounter quantum theory, they go through several stages. The first stage, which is about 6 months, is learning how to use the mathematics of quantum theory to make predictions. And this stage is relatively easy and painless. And then students enter a second stage where they suddenly realize that they don't understand what they've been doing. They don't understand exactly what this mathematics is supposed to be saying about the world. They get very confused. And this is a very difficult period for students, and it can last 6 months or longer.
5 stages of grief with quantum theory.
Right. Yeah, exactly. The 5 stages of grief. But then at some point, if the student is successful, the student reaches a new level of understandings, the third stage, where the student realizes that there is actually no question at all. There's nothing, this is exactly how he puts it, there's nothing to be understood. The student has now begun to think fully in the sort of quantum way of thinking, and is ready for like the next stage. And Dyson, in this 1958 essay, he argues that he believes that the second stage, the confusing stage, the stage where the student is still hanging on to pre-quantum classical ways of thinking about the world, Dyson argues this stage is shrinking with each passing generation, and eventually one day it will disappear completely, and then we will be ready for the next stage in the evolution of science. This was a staggeringly bad prediction. Dyson was a brilliant, very important scientist, but he did say some things that were wrong, and this was completely wrong. For one thing, this was 1958. Quantum theory in its modern form had been around for a couple of decades at that point. That's basically one generation. He was a theorist, and maybe the experimentalists watching this will laugh and think it's just like a theorist to generalize based on an n equals 1 example, right? He basically had one generation he was working from. But we've also now had almost 70 years since that essay, and that stage hasn't gone away. Every generation, students come in and they're just as confused as the generation before. And sometimes their teacher will still tell them the same thing. You just don't understand quantum theory well enough. One day you'll understand it. Now, of course, not all teachers say this. Some are very open about the idea that there are mysteries still in quantum theory.
There's a shut up and calculate phenomenon that's predominant.
Yeah. David Merman is the one who's responsible for that phrase. He did not use shut up and calculate in a positive way.
Yeah.
He was being quite negative about it. It was in an essay, I think, in Physics Today, I think in 1989, called What's Wrong with This Pillow? Which is kind of a funny name for an essay, but where he coined that phrase. But the thing is, when we look at our physical theories, where they break down, sometimes this suggests areas of further study, and sometimes it can mean that it's a stepping stone to a better, deeper, more useful, more powerful, more comprehensive theoretical description. People have thought about the singularities in other theories before, and Okay, so sometimes we don't come up with a better theory. Sometimes we discover we need to think differently about the theory, but sometimes we discover that there is in fact something there. Something there. The theory has a crack in it. What's that Leonard Cohen line? There's a crack in everything. That's how the light gets in. Right? Sometimes there are cracks in your theory and light gets in, sometimes light comes out. Sometimes it's worthwhile to look at our best physical theories, look for all the cracks, and examine them really carefully. Sometimes you'll find nothing, or you'll find the crack was a mirage, or the crack doesn't contain anything particularly interesting or can be filled in. And sometimes you discover a nugget of gold inside.
There's a Rumi quote which says, "The wound is where the light enters you." A more poetic way of saying the same thing.
That's delightful. I love it. It's great. That's great.
It's a bit of Sufism. Okay.
I love it. It's great. It's beautiful. So one of the basic motivations for someone to do the kind of work that I work at the intersection of philosophy and physics. I was trained in high energy theoretical physics. That's what I did my PhD here at Harvard in. And toward the end of my PhD and then beyond, I've moved more into philosophy. And now I see myself doing both philosophical physics and physical philosophy. Philosophical physics is using many of the methodologies and tools that come from philosophy, in particular analytic philosophy, to try to make progress on important open questions in physics. And in physical philosophies, using what we've learned about physics to try to say something useful or make progress on traditional questions in philosophy. Part of what philosophical physics is looking for those cracks in our theories. Looking at our theories as honestly and clearly as we can, and trying to identify any place where they don't fit together quite right. Sometimes we find nothing, but sometimes we find something. And there's a proud tradition of this. I mean, the most famous example is Einstein himself, who saw some cracks in the way we talk about frames of motion in our before 20th century physics, and realized that in those cracks out came the theory of relativity. Now, there have been many responses to these sorts of problems with quantum theory over the years. One response is to say, well, quantum theory, the axioms also give you averages. The axioms let you say, on average, a certain property will be like this or a certain property will be like that. There is a textbook by Ramamurti Shankar. Shankar is Shankar. It's a big pink book. It's a lovely book, very beautifully written. I'm very much a fan of it. It's an excellent book for self-study in particular. I've known students who've taught themselves undergraduate and graduate level quantum mechanics just from reading this book and doing all the problems. You have to do the problems. But the book has an entire chapter 6, that's called The Classical Limit, that's devoted to the idea that the averages that we get from the axioms are enough to explain how classical phenomena happen, the emergence of the classical world. And this is based on a mistake. Because the averages we get from the axioms are not averages of phenomena happening. They're not averages of the kind where we look at, say, a box filled with 1,000 marbles, and the marbles are all flying around and they fall out of the box, and we can say on average what the marbles are doing. They're not that kind of average. They're not the kind of average that Einstein was thinking about when he was thinking about Brownian motion. Brownian motion is this observation that grains of pollen in water kind of dance around in this very strange way, and Einstein was able to account for this by talking in terms of atoms in the water bombarding the pollen. And because of the way statistics works, you get these patterns of bombardment that can lead the pollen grain to dance in various ways. And you can capture the behavior of the water molecules using averaging techniques. But these are averages of things happening. We can't say exactly what each water molecule does, but we can say on average what they do. These are happening averages. The averages we get out of the axioms of quantum theory are not those kinds of averages. They are averages of measurements. They are numerical measurement outcomes, statistically weighted by the probabilities with which those measurement outcomes occur. And that's a mouthful. I just said a mouthful, but it's important to say that mouthful because it makes clear that just because it's an average doesn't mean it's the kind of average that you're hoping to find in a correspondence to classical physics. I remember spending a tremendous amount of my time as an undergraduate reading material like this, reading chapters like this, and just feeling like it didn't quite connect. I could almost see how the classical world was supposed to emerge from the averages, but because you needed measurements and measured outcome probabilities to build these averages, they didn't seem like the kinds of averages that described phenomena really happening in the world. I couldn't bridge the gap. And I couldn't bridge the gap because the gap is not bridgeable from the axioms. So if you're a student who struggled with trying to understand how averages are supposed to turn into phenomena happening, you're struggling because it doesn't quite work. It's not merely a matter that you need to get more mature or sophisticated about the theory, and then it just doesn't quite work, and we should be honest about this. Now, there are other ways to write the axioms of quantum theory. For example, you can combine the axiom for how quantum states change, the unitary time evolution axiom, and the measurement axiom, at least in a particular context, a particular kind of thing you're measuring, to get what's called the path integral. The path integral. So there's a video on YouTube right now. I'm going to make a comment about it because I think it's important. It's a video by the wonderful YouTube channel Veritasium. And it's all about the path integral. And it has millions of views. The path integral says that one way to calculate these mathematical facts, these mathematical empirical facts, is to imagine that your system, let's take the system for simplicity to be a particle, if that's the system we want to describe, to imagine this particle could take any possible path from point A to point B. And this is now referring back to that picture I said about, does quantum theory tell us the particle takes every path? Imagine the particle is taking every path. Assign to each path a certain kind of quantity, a certain kind of number. It's called a phase factor, a complex phase factor, but doesn't matter, a certain kind of quantity. Assign every single path this quantity, every conceivable path you can imagine. Paths that behave in ways that don't make any classical sense. Every path you can imagine that goes from point A at the initial time to point B at the final time. Assign all the paths, each path one of these numbers, and then add all the numbers together. Now, there's a continuous infinity of these paths, so adding the numbers together is a little bit mathematically tricky, but there are procedures to do this sum, to do this, we call it a path integral, this sum over paths. And when we add all these numbers together, we get a final number. And this final number is still a complex number. And then we do a certain kind of operation. It's called mod squaring. And this mod squaring gives us the probability. But the probability of what? Not the probability that the system will go from point A to point B. The probability that if we have prepared it with an appropriate measurement and found that it was at A at the initial time in our measurement, then this is the probability that a subsequent measurement at the later time, the given later time, will find it at point B. These are still measurement probabilities. They're not probabilities of things just happening. The axioms don't provide us with that sort of a thing. The claim that because we can do this technique to get the answer is telling us that the particle is really following all the paths simply doesn't come out of the axioms. It's not in any of the Dirac-von Neumann axioms. And the derivation of the path integral, which goes back to a paper by Paul Dirac in 1932 called the Lagrangian in quantum mechanics, and then was later developed into a more precise set of mathematical tools by Richard Feynman in his PhD work in 1942, and then presented more broadly to the physics community in 1948 in a more extensive journal article. The fact that it's a convenient mathematical technique for getting those results doesn't mean that it's telling us that systems are really doing this. Again, the Dirac-von Neumann axioms don't tell us what systems are doing in a physical sense between our measurements. What's worse is that to define the path integral as this mathematical thing, this mathematical procedure, you often have to modify the parameter playing the role of time between the initial time and the final time. In order to get the mathematical sum to give you a well-defined result, you often have to give time a small imaginary part. A small imaginary part. So imaginary numbers that are the square roots of negative numbers, They're kind of formal number-like quantities that we can often use like numbers. Time seems to be real valued. In order to make this mathematical function well-defined, to make this integral over these highly oscillatory complex phase factors converge, as they say, you often have to give time a very small imaginary part. You do the calculation, at the end you attempt, if possible, to take a limit in which the imaginary part goes to zero. I don't know what the heck that possibly means. But it doesn't bother me, because as long as you don't regard the path integral as literally telling you what the system is doing, but merely regard it as a convenient mathematical tool, then you're not going to be bothered by this. Now, I should say that in the past, there are physicists who've tried to make claims that imaginary time makes fundamental sense. One of them was Stephen Hawking, who wrote about imaginary time and tried to explain that imaginary time was sensible and a real thing and things really did this. But this is certainly not a consensus view, certainly not my view. And there's nothing about the axioms of quantum theory that compel us to take that view, merely because this mathematical technique works so well. So we've talked about attempting to use averages to get at the classical limit. We've talked about path integrals. How do path integrals connect with a classical limit? Well, there are various arguments that in certain circumstances, some paths matter more than other paths do. There's a line in Orwell, in Animal Farm. All animals are equal, but some animals are more equal than others.
Yeah.
All the paths contribute the same kind of phase factor. In the complex plane, all phase factors have unit norm. However, some paths matter more than other paths do. And in some circumstances, you can argue that some paths make a much bigger contribution to that mathematical result, that we could ignore most of the paths and only focus on a few of them. And in certain circumstances, when we have a situation in which the paths that matter the most, in fact, matter the most, it turns out those paths are often very similar looking to the paths the system would have taken if we'd treated the system classically. But this does not mean that this is how the classical limit arises. It does not mean quantum theory is telling us that the system is truly taking that path. It's merely a mathematical statement that one path has the most significant contribution to this integral over the other paths. Yeah. This is not a route to understanding how the classical limit arises. So with all, respect to Veritasium, which I am a huge fan of, I think it's a little misleading to paint the picture that path integrals are somehow telling us exactly what nature is doing. At the very least, that requires a leap of interpretation that is not inevitable and not required. It's a particular interpretational stance and not necessarily something that is definitively implied by the axioms of quantum theory. Okay, there have been other attempts. One is to cite something called decoherence. Mm-hmm. And this, unfortunately, gets a little technical. Why do we need to patch up quantum theory? Doesn't decoherence resolve all these problems? Doesn't decoherence allow us to determine in realistic situations when a certain kind of interaction counts as a measurement?
What is decoherence?
Is it? What is decoherence? It's interesting to think that because of decoherence, we don't have to ask interpretational or philosophical questions, given that decoherence arose from philosophical interpretational questions. Decoherence was introduced by David Bohm. David Bohm thought a lot about interpreting quantum theory. He's in part responsible for one of the major interpretational stances toward quantum theory, pilot wave theory, which he independently discovered separately from Louis de Broglie. This is now known as the de Broglie-Bohm pilot wave theory, or Bohmian mechanics for short.
Yeah.
How did he discover decoherence? He was trying to understand the measurement process. He was writing a book, a textbook, called Quantum Theory, which you can buy. It's on the shelves. There's a Dover edition of it. It's delightful. It's from 1950-51. And it's a fairly conventional treatment of quantum theory for the most part. But then at the end of the book, chapter 22, he starts trying to probe the measurement process. He wants to find a better way to explain the measurement process, to explain why it happens in a way that doesn't require so much hand-waving. And in section 22.8, which is called The Destruction of Interference in the Process of Measurement, he lays out a detailed picture of the measurement process. A measuring device comes into your system. It's treated like a quantum system in its own right.
Mm-hmm.
The measuring device comes in, interacts with your system, and enters what's called an entangled superposition, which just means that at a level of mathematics, you had some very strange looking quantum state for your system. The measuring device comes in. Now you describe the whole thing with one big quantum state. And this quantum state appears to look like a blend or superposition of terms. In the first term, you have what looks like the quantum state of your system to be measured having a certain property and the measuring device recording that property, blended with another term that looks like on its own, if it were on its own, the system being measured having a different value of the property and the measuring device recording that value of the property, blended with another and another and another. We call this an entangled superposition. It's a blend across quantum states, and in each quantum state, it looks like the measuring device has recorded a definite result and the system has a definite value of that property, and we've added all these together in some strange superposed sense. And then what Bohm shows is that if the measuring device is sufficiently complicated, and I don't remember if he includes the environment as well in this story, probably, but I don't quite remember all the mathematical details of this section. He shows that these terms start to behave mathematically more and more independently as the measurement process proceeds. And eventually they're so independent, they're so non-interfering that we can treat them like separate realities. And at this point, there's no interference. The interference has been destroyed. They have decohered. We have what's called decoherence. Bohm discussed this with Einstein, and this is 1951. Bohm was in Princeton. Einstein was in Princeton. And Einstein was dissatisfied. And after some extensive discussions, Bohm realized he was dissatisfied too. This person who discovered decoherence realized very quickly, although it did take a conversation with Albert Einstein, that decoherence was insufficient to resolve the measurement problem. For one thing, at the end of decoherence, you still have not singled out one answer. You still have all of these answers. How do we get from these many answers to one definite answer, which is, of course, what we see when we do the experiment? Now, of course, one attitude is maybe there isn't a definite answer, and this leads to the Everett approach, Everettian quantum theory, now popularly known as many worlds theory, although Everett didn't use that term for it, at least not initially, at least. But Bohm's...
I'm sorry, many worlds is every single path exists.
That's the many worlds,
many worlds
attitude, yeah. Bohm did not take that view. Bohm wanted to find some way to get a definite result, which is, of course, empirically what we see, not a blend of all the possible results. And that's what motivated him in part to introduce his pilot wave theory, which he introduced in a pair of papers in 1952. The first paper has only one acknowledgement. It just acknowledges Albert Einstein. In the second of those papers, he goes through the measurement process in great detail and explains how his pilot wave theory is able to resolve the measurement problem, give a clear explanation of what is happening in the measurement process, what's special about measurements, and is able to explain why we get a different result. In that way, it resolves the measurement problem. In some sense, one way to think about the measurement problem from the point of view of Bohm's work is when a system encounters a measuring device and the measuring device does a measurement, we end up, if you apply the unitary time evolution axiom, but not the measurement axiom, it's just the unitary time evolution axiom, it looks like the system and the measuring device enter a kind of entangled superposition. But then somehow this superposition collapses to only one of the terms. And it collapses in a probabilistic or chancy way. With some probability given by the Born rule, one of them is realized and the others are not. What is the special feature or property or attribute of measuring device that leads it to fall out of superposition, to bring down the house, to bring down the superposition and collapse it? Why is it that some systems can collapse these superpositions and others cannot? What is it about measuring devices or observers that have this capacity? That's the measurement problem. And the way that Bohm got around it was to say that actually there always is a result. Particles always, in fact, have some underlying value at all times. No particle is truly ever superposed between two possibilities. That was his interpretational stance, and it means right away that if you're going to claim that quantum mechanics is definitively telling us an atom is in two places at once, Bohm would disagree. In Bohm's picture, the atom is in one place. There is a particle in one place and not the other. And the fact that we use these superpositions is either because we're talking not about the particle, but we're talking about the pilot wave itself. The pilot wave itself can be superposed, but the particle is not. But in more modern formulations of Bohmian mechanics, but not by consensus, there's still some people who take a different view, but some of the more modern formulations of Bohmian mechanics that go back at least to the 1990s by people like Shelley Goldstein and Detlef Durr and Eno Zangi take what's called a nomological view of the pilot wave. The pilot wave is not a physical object. The pilot wave is merely a kind of law, a mathematical law. This goes way back to our conversation of mathematical laws. It's a piece of mathematics. It's just mathematical language that describes the behavior of the particles. And so the fact that this mathematical object can have a superposition doesn't tell us anything in physical reality is in a superposition. It's just telling us a certain thing about the pattern of behavior of the particles, which are only ever in one place at a time.
Gotcha.
So if anyone thinks that decoherence alone can resolve the measurement problem, they have to contend with the person who introduced decoherence, who certainly did not think that. They also have to contend with the fact that the person who introduced decoherence was interested in interpretational questions, was interested in the measurement problem. So if one's attitude is, we don't need all this philosophy, we don't need all this interpretation, we have decoherence. Decoherence was clearly given to us by physicists. Who needs the philosophers? Well, David Bohm, in some sense, was wearing his philosopher hat. One could make this argument of whether he was really being a philosopher or whether he was being a physicist at the time. But I think it's unquestionable he was interested in interpretational problems when he devised this idea of decoherence. And if you think decoherence is important, and it is, it's very important. Decoherence timescales are now in practically every paper on quantum computing that anyone ever writes down. People are trying to build all kinds of tabletop quantum systems and quantum hardware. They're talking about decoherence timescales all over the place. Then you credit all of that to someone thinking about those cracks in our theory, looking in those cracks, and in this case, finding a nugget of gold. So if there was ever a good advertisement for that, it would be something like David Bohm's work. And arguably, we should be continuing that work, looking for cracks and trying to discover what's inside of them. Well, if decoherence is unable to single out one definite outcome, well, then it clearly by itself can't work without some kind of interpretational step. One is to suppose, as Bohm did, that the system really does have some underlying value, at least for some of its properties. There are theorems like the Cauchy-Specker-Nogor theorem that says you can't assume that all the properties have pre-existing values, but at least some of them can. That's fine. But another view is to say that maybe all of those terms represent actual physical realities. This is clearly what Hugh Everett said. Hugh Everett, working in 1956, 1957, also at Princeton, under the advising of John Wheeler. Eugene Wigner was also there at the same time. Presumably they had many conversations about all of this. And although there's some dispute over whether Everett liked to think of all these terms as many worlds, he certainly did talk that way. He had this analogy, the amoeba analogy, in which he talked about how when your measuring device goes from its original quantum state to breaking up into all of these parallel versions of itself with different observed values, he analogized this to an amoeba splitting into daughter amoebas. He talked explicitly about how his picture denied the uniqueness of the observer. So whether he was thinking in terms of fully fleshed out parallel realities, he certainly had in mind the idea that observers were somehow splitting like amoebas. Yeah. He talked this way. This is in his writing.
Right.
Although the actual language of many worlds came later with people like Bryce DeWitt, who began as a skeptic of the many worlds approach, but eventually became one of its strongest advocates. In an article in 1970 in Physics Today, Quantum Mechanics and Reality, that presented the many worlds theory to the wider physics community. Hugh Everett came out of retirement then and went on a short lecture circuit before, unfortunately, he died an untimely death. But he certainly seemed happy with what people were saying about his theory. He had left physics in the meantime and come back, as his theory was getting a lot of attention, decades after he'd originally introduced it. What's the problem with the many worlds approach? Well, if you take all those branches to be equally real, all those terms in the superposition, and you imagine that the measuring device measures the system, now you've got copies of the measuring device and all these branches, and then the environment comes in and looks at the various copies, and the environment splits into branches. And you imagine there's this unzipping process where the whole universe just gradually branches and branches and branches, and more things join the branching and split. The observer gets a certain answer and splits. You talk to the observer, you split. Your friend talks to you, your friend splits, and you just get all these parallel copies of observers forming these macroscopic world branches. Does this provide us a viable way to resolve the measurement problem? Well, we can have an extensive discussion about the many worlds approach. I've had that discussion in other places. If people are interested in my views on the many worlds approach, I would recommend they look at some of the other videos on YouTube where I talk about this more extensively. What I'll just say briefly here is that there are problems with the many worlds approach. What singles out a particular way to break up the overall quantum state into branches is a question called the preferred basis problem. A quantum state is a vector. In the simplest cases, it's a vector. And a vector can be expressed in many, many different ways, in different choices of basis. In fact, infinitely many different ways. And each of those choices would describe what look like different branched realities, like totally incompatible, totally different kinds of branched realities. What singles one out over all the others is unclear, at least when you first look at it, at the many worlds approach. In somewhat more sophisticated analyses of the many worlds approach of Everett's theory, one appeals to decoherence. One says that as you let the quantum state evolve, there will be a particular basis, a particular way of describing the system, a particular way of breaking up the universal wave function, the universal quantum state. There'll be some particular way to do it in which you get clean branches that are approximately no longer interfering with each other, that describe reasonably well-defined macroscopic realities. And so decoherence is what singles out a preferred way to decompose the universal wave function or the quantum state of the universe. Now, this does arguably resolve the preferred basis problem, but it comes at a cost. The cost is that now your branches are not fundamental ingredients of the theory anymore. They're approximate emergent ingredients. Just like we were talking before about how a chair is not fundamental. A chair may exist, but a chair is really not a fundamental thing. It's made of more fundamental things. If you have a theory of chemistry, let's say, and your theory of chemistry has basic ingredients, atoms and electrons, let's say protons and electrons, neutrons, that's your theory. And we're going to, for the purposes of our theory of chemistry, pretend that they're somewhat classical like objects. Let's just pretend for now. You've got some theory in which those are your basic ingredients. You can give them properties. You can give properties to your fundamental ingredients in the fundamental axioms. And you can certainly have objects like chairs emerge in some situations, in some circumstances at later stages of your theory. Your theory describes the atoms moving around, and in some circumstances, those ingredients will combine to make things like chairs. And the chairs are there. They can be perfectly there. And the chairs can have properties, but those properties have to be grounded. They have to be made out of the things you took to be your basic assumptions. You can't, once you have chairs show up, then by hand attach properties to chairs from outside of your theory.
Yeah.
Any properties the chair has have to follow from the properties of the basic ingredients, those properties of the basic ingredients being specified in your axioms. Yeah. You can't, once you have chairs, then add on an axiom saying, now that I've got chairs in these circumstances, I'm going to add some additional axioms that give chairs certain properties.
You have to be grounded in those axioms.
Exactly.
Yeah.
And this is where we run into a problem. Mm-hmm. If the branches are not fundamental, if they're like chairs, we cannot give them properties in the axioms anymore. And one property we really want to give them is probabilities. You see, once you have all these branches, nothing is collapsing and no one result comes out. What do we even mean by probability anymore? What you can try to argue is, well, maybe we don't know what a probability is, and we'll talk a little bit about probability maybe, okay? And I should say, by the way, there are other questions, like how do we even know that decoherence singles out a unique basis anyway? Maybe decoherence doesn't do it, or maybe it singles out too many. But even putting all those things aside, if we want these branches to have some notion of probability, we either have to put probability into our axioms, but we can't do that anymore because I can't assign probabilities to approximate immersion things in my fundamental axioms, as I've just explained. Yep. They're not fundamental. They can't get properties in my fundamental axioms. And I can't just add on later on probability properties later to the ingredients that sometimes contingently show up in the development of my theory. Mm-hmm. So my other option is to try to somehow derive probability without making probability an assumption. Somehow get probability to show up from non-probabilistic axioms or premises. And this can't be done. It just can't be done. There's an old problem in metaphysics, ethics actually, going back to David Hume, called the is-ought dilemma. Is and ought or should. For people who want to come up with a completely logical reason why, let's say, you ought not steal. You ought not steal things that don't belong to you. You'll have some argument that looks like, well, to steal is to take something that doesn't belong to you, something like that. That's premise one. Notice it's an is premise. To steal is to do this thing. But how do we get from that premise to you ought not steal? Somewhere you have to say, premise two, you ought not take things that don't belong to you, and then combined with to steal is to take something that belong to you, and then you ought not take things that belong to you, you can arrive at the conclusion, therefore, you ought not steal. But you can't get to an ought from an is. And people have been arguing that you can for a very long time, even today. People who argue that somehow ethics can be derived purely from scientific reasoning, that there's like, that certain ethical frameworks are just scientifically true. They all, at some point somewhere, commit the is-ought fallacy. It's not a matter of just waiting for better philosophy to come along. You just can't do it. And the same thing happens with trying to get probability out of assumptions that don't begin with probability. And I'm not the first to point this out. John Norton, philosopher of science at University of Pittsburgh, has pointed this out repeatedly. I believe he points this out in his Material Theory of Induction, in a book that he wrote. I think that's where it was. That a deductive argument, a logical argument that begins with premises, can arrive at a conclusion, but that conclusion cannot be any fundamentally stronger than the premises that you started with. If you don't have probabilistic assumptions, you can't get a conclusion about probabilities. Nonetheless, people have been trying to do this for a very, very long time. It shows up in Everett's original thesis, both the original long-form version of his thesis and also in the shorter version, where he tries to argue that, well, if there were probabilities, then the only one that would work would be the Born rule probabilities. But this doesn't really resolve the problem. In the years since then, people have tried more and more sophisticated versions of these arguments, and they're ingenious arguments. And I think very highly of my colleagues who work who advocate for the Everett approach. I mean, they're brilliant and their papers are fantastic. And I've learned a tremendous amount. I've read almost everything. Like, I've learned a lot from engaging with this literature. They're doing incredible work. But I would argue that it is precisely because they're so brilliant and because they're so careful and rigorous that the fact that they can't succeed is precisely telling us that there's a problem here. What you find in all of their arguments is either logical circularity. At some point, they assume a thing that was to be proved, or you get a very long list of assumptions that cannot be empirically studied, extra empirical assumptions, or I call them speculative metaphysical hypotheses, or SMHs, and the acronym is very intentional. And I talk elsewhere about this stone soup metaphor.
Yeah.
The claim is that there's just a few simple principles and then everything else follows. But if you actually carefully read the arguments, and I always tell my students,
add the seasoning, add the meat.
You got to add all these little ingredients,
Yeah.
and before you have a great soup, but it turned out there were all these ingredients you needed. But I would argue that it still doesn't quite work. At some point, you had to assume an ingredient that had probability in it, which is not legal because the things you're trying to attach the probability to are emergent things. So at some point, you had to actually do something you weren't supposed to do.
Mm-hmm.
And I have yet to see an argument that ultimately gets around this problem because I just don't think you can. And elsewhere, I've made, specific arguments about particular attempts to do this. And there are different attempts. Some use what are called rationality axioms and decision theory. Some use various forms of coarse graining and then counting branches. But all of them at some point entail, and therefore we can now assume that something is either equally likely to something else, or we can use a symmetry and say that these things, because they're symmetric, they have certain probabilities, or we can say that what it means to be a rational observer is that you should assign probabilities in a certain way. But ultimately, if you just look at the multiverse picture that they're describing, you just see a huge number of branches. And on those branches, some people are rational and some aren't. And whether they succeed or not, there are branches in which the rational people succeed in the long run, and branches in which the rational people don't succeed, and branches in which the irrational people succeed, and branches in which they don't succeed. There are branches of every kind, and they're just there. And sure, there are some observers in some branches who will decide to assign probabilities according to the Born rule, and there will be other observers who don't. There'll be some observers who do and they get the right answers, and branches where they do and they get the wrong answers, and branches where they don't and they get the right answers. I mean, they're just all there, trying to somehow turn these arguments around and go from being rational to these arguments are ultimately all circular. And I say this having engaged with all the people working on Everettian quantum theory. And I, at the very least, there's still a significant amount of work to be done to make a compelling case here. I mean, one can never be sure in philosophy. There's always the possibility that someone will come up with a really ingenious argument that we haven't thought of before that will finally solve this case. But I don't think it's just a matter of we just need better philosophy. I think when you run into an obstruction like this, the answer is not to say the physics is clearly telling us that there's a many worlds multiverse, and we just need better philosophy to explain how it works. That's not how philosophy works. We don't start with the goal and then construct the philosophy to fit the goal. Philosophy is exploration. It's the pursuit of knowledge. You follow that knowledge where it takes you. You don't start with the goal and then construct a philosophical argument to get there. That's not philosophy. That's lawyering. It's not the same thing. So look, in the absence of a compelling interpretation that meets some basic minimal criteria, I think there's room for something new. The many worlds interpretation comes from the 1950s. The pilot wave theory comes from de Broglie in the 20s and then Bohm in the 50s. I should have said that the problem with Bohmian mechanics is that no one has found a satisfactory generalization that's able to accommodate the kinds of quantum field theories that we actually encounter in the standard model. Bohmian mechanics helps itself to a number of what seem like very, very special features of systems of fixed numbers of finitely many non-relativistic particles, in which it works quite beautifully and has a beautiful correspondence with what's called the Hamilton-Jacobi formulation of classical physics, which is actually where wave functions came from originally. It's how Schrödinger introduced them in 1926. But the attempts to generalize Bohmian mechanics to quantum field theories, and in particular to certain kinds of quantum field theories called fermionic quantum field theories, the kind that underlie particle-like excitations that we call electrons and quarks, this has proved very, very difficult. And I have some really wonderful colleagues who are working on this right now. I've already mentioned a few of them, Goldstein and Zangi, but also people like Ward Struve, who I've read most of his papers because they're delightful and really very interesting. But his papers also, I think, make clear just how hard it is to try to get Bohmian mechanics to work in these circumstances. I'm not saying you can't possibly get Bohmian mechanics to work in some form in these circumstances. I mean, if there's a will, there's a way. If you're willing to work hard enough, you'll eventually get there. There's an old saying in statistics that if you torture the data will confess. Okay? If you work hard enough, you can get almost anything to work. But at some point, I start developing this kind of uncomfortable feeling in the back of my neck that I'm working too hard and that nature is telling me this is not right.
Okay.
When you have to work too hard to make something fit, it's like trying to get the proverbial square peg in the round hole, the round peg in the square hole. I forget which it is.
To hammer everything looks like a nail.
To hammer everything looks like a nail, exactly.
Yeah.
If you have to work that hard, it just doesn't feel like what you're doing makes sense. It's missing a certain kind of naturalness. That was characteristic of the Bohmian mechanics in the case of fixed numbers of finitely many non-relativistic particles, where it does work quite beautifully.
Okay.
And people make arguments, well, even in that case, there's like non-locality. But I mean, it makes the same empirical predictions as anything else. I mean, so whether it has an aesthetic property of non-locality is I guess, maybe a problem, but it's not a deal breaker as long as it makes the correct empirical predictions, which it does in that limited set of physical circumstances. We just don't have a good, compelling version of Bohmian mechanics for more general kinds of physical theories. Now, there are other interpretive frameworks people are working on. And some of them take, different views. There's, of course, the Copenhagen interpretation, which was first given its name, as best I can tell, in an essay, in a chapter called The Copenhagen Interpretation of Quantum Theory by Werner Heisenberg in his book, Physics and Philosophy. It's funny that so many physicists took philosophy so seriously, especially physicists who gave us quantum theory. Maybe that tells us something important, that we should embrace philosophy in physics. But that chapter, he lays out what he takes the Copenhagen interpretation to be, and there is some dispute over exactly what the Copenhagen interpretation is, but his view of the Copenhagen interpretation is there are classical objects like us, and there are microscopic objects that are quantum, and we cannot, with our brain architecture, understand what's going on fundamentally with quantum microscopic objects, but we can assign them mathematical things like wave functions, quantum states, and we have rules for how those quantum states change, but we should regard those things as just mathematics, just description, just in our heads. The wave function is not a physical thing. It's just a thing in our head. And we just use it as a tool to predict what classical things like us will see when we probe quantum systems. He's very clear on this is what's going on, at least according to the Copenhagen interpretation. But this immediately rules out the possibility that quantum theory can apply to big objects. Because by definition, there are classical objects that do not obey quantum theory. We have a classical theory for them. And microscopic objects for which we use quantum theory. But this, again, rules out the idea that quantum theory applies to everything. It applies to big objects as well. So that has limitations too. And there are, other interpretational variants. There's quantum Bayesianism or cubism. There's a transactional interpretation. There are various retrocausal interpretations. There's ensemble interpretations. There are a lot of different interpretations. Yeah. I still think that we have a gap. And there's room for one that meets what I consider to be deal-breaking criteria. And here are my criteria. Just lay them out. The first is empirical adequacy. Your interpretation has to be able to handle the kinds of quantum systems that we actually use and make the right predictions. In that respect, so far, Bohmian mechanics doesn't quite meet that standard. There are also some collapse theories of quantum theory that arguably we haven't been able to generalize in the right way, and some of which have been empirically ruled out already. So empirical adequacy is just a base requirement. And I would argue that even with as many additional assumptions as you try to bake in, if you're being careful and honest, you can't get the right probabilities out of the many worlds interpretation. And the probabilities are the empirical content of quantum theory. And if we can't get them out of the many worlds approach in an honest way, then even the many worlds approach doesn't succeed at the level of empirical adequacy. Your approach shouldn't be vague about important, like the things it's trying to say. I mean, certainly if your theory doesn't say some things, fine. But if theory is trying to say some things, but there's a lot of hand waving, oh, we mean records or measurers or observers, and we're just like hand waving away what these things are, that's not so good. And in the Copenhagen interpretation, we see this very clearly. What is a classical object? When is something classical? That's kind of vague. When does something go from being microscopic to classical? That's vague. So vagueness is a problem. There shouldn't be ambiguities for big systems. And I'm going to, in a moment, come back to the Wigner's friend thought experiment, which will explore that. I'll come back to that point in a moment. But basically, your theory should make unambiguous predictions about what will happen. Textbook quantum theory, the Dirac-Feynman axioms, are reasonably unambiguous when we're studying microscopic systems. But when the systems get bigger and bigger, we eventually begin to run into ambiguities about what's supposed to be happening with them.
Yeah.
And those ambiguities are the singularity I was describing when I said that the Dirac-Feynman axioms have a serious problem. Separately from what is a measurement and the category problem is just what do we do in certain circumstances. These circumstances do seem to matter in some physical contexts. When you want to apply quantum theory to astrophysical problems, when you want to apply quantum theory to black holes or the whole universe, quantum cosmology, for example, string theory, quantum gravity, whatever you're interested in, you need to apply quantum theory seemingly to big systems. And that's exactly where we run into these ambiguities. And when you read papers in high energy theory, sometimes they run headfirst into these questions, these ambiguities about what is quantum theory supposed to be telling us is happening with big systems. So that's a real problem that needs to be addressed. So far we have empirical adequacy, we have not having the vagueness, we have unambiguous predictions. There shouldn't be an endless list of speculative metaphysical hypotheses. So that's also an important requirement that we should place on our theories as well. So arguably we shouldn't have that either. So I regard these as like really deal-breaking problems, right? If your theory doesn't meet these requirements, we have a significant issue. And arguably none of the interpretations we have so far meet that minimal set of requirements. Notice I haven't pointed to aesthetic conditions. I haven't said, well, the theory isn't symmetric enough, or it looks like it's a little bit in tension with special relativity, or it looks too non-local, or it doesn't obey Occam's razor. It's not simple enough. You know, of course, I did say it shouldn't have an endless list of additional hypotheses, but and maybe in some sense that's a bit like Occam's razor, but it's a very weak form of Occam's razor. So I think there's room for something new, and this is where I think my work is intended to come in.
I think this is a good point to introduce your framework that you find compelling and you feel addresses all these criteria. Let's talk about indivisible stochastic processes, but I must remind you, I'm still a 12-year-old.
Okay, good. You're a 12-year-old. Okay, let's do this. Okay. So let's go back to our picture. There's phenomena, things out in the world behaving in various ways, and we want to use mathematical rules to describe what they're going to do and make predictions about them. The phenomena appear to exhibit patterns. We want to capture those patterns using mathematical language, and then we want to use that mathematical language ideally to make predictions. We've talked about how sometimes those rules can be deterministic, tell you exactly what's going to happen, and sometimes they can be probabilistic. Let's consider a system, a thing, a kind of thing out in the world that's doing things, exhibiting various patterns. And let's suppose that the best we can do to capture the patterns we see is to assign probabilities to some of those patterns. Okay? We've got an object of some kind. It can be configured like this or configured like that. It can be here, it can be there. We call these different possible configurations. And this thing is behaving in kind of a strange, somewhat unpredictable way, but we can assign probabilities in some cases to how it will behave. We can capture its behavior using probabilities.
Okay.
these probabilities could be, what's the probability right now that it's in this configuration versus that configuration? And some of these probabilities instead look like, if it's in this configuration at this so-called conditioning time, this starting time if you want, given that, then what's the probability that it will be in that configuration?
Conditional
at
probability.
that target time. We call that a conditional probability.
Yeah.
And suppose we have a bunch of those too. And that's it.
I must point out these are classical probabilities, very different from those measurement probabilities you pointed out earlier with the wave function.
I haven't used the word measurement here. I'm saying these are probabilities of what configured system is in.
Yeah.
We call those standalone probabilities. And then conditional probabilities, probabilities of the form given or assuming it is in such and such configuration at this conditioning time.
You're redefining the picture with just classical probabilities.
These are all classical. Well, classical is a bit of a tricky word. I would call them ordinary probabilities.
Ordinary, okay.
Because if you think classically, maybe think Newtonian mechanics. Newtonian mechanics describes things using deterministic laws.
Yeah, I see the confusion.
The word classical has a physics meaning. Let's just say ordinary probabilities.
Ordinary feels demeaning, but we'll work with it.
Ordinary. How about
conventional? Maybe.
Conventional has somewhat. How about old school?
Old school.
Old school probabilities.
Vintage probability.
Vintage. Oh, great. Vintage probabilities.
I hope the term sticks, and this is the
place.
This is
vintage
the place.
probabilities. These are vintage probabilities.
Okay.
They have the usual rules of vintage probabilities. They are good old fashioned ordinary real numbers that go from 0 to 1. They sum to 1. You can marginalize. You can do all the usual ordinary vintage things with them. Good. And that's it.
Mm.
And you're like, well, what do you mean that's it? Well, what else? Yeah. What are their ingredients? What are the laws? And I know the laws. That's it. That's what we're saying. We're saying we have a model in which all we know are the standalone probabilities, maybe at every time, and we have these conditional probabilities that connect pairs of times. Remarkably, this kind of a model can be re-expressed in the mathematical language of Hilbert spaces. And when one does so, one arrives at the same axioms you get in textbook quantum theory.
Can I take a digression? Why wasn't it done? Because we were aware of this vintage, old school probability theory. Why did they invent this new system of probabilities when we had this already?
So we had old-fashioned probabilities, but people assumed that in any reasonable model that used probabilities to describe the behavior of systems, that you had to be given probabilities for everything. You had to be given the probability that the system will be in such and such configuration at this time, and such configuration at that time, and such and such configuration at that time, and such a configuration at that time, and that conditioned on that, that it's in such a configuration at this conditioning time, and that it's in this configuration at this other conditioning time. And people assume that you had these very, very, very extensive so-called joint probability distributions. That you could assign probabilities to the configuration the system is in at large numbers of times. Now, that's a lot of different probabilities. It's a huge number. In fact, it's infinitely many distinct probabilities that you would need. And so in practice, people would rarely try to formulate a model this way. What they would do is they would say, okay, well, maybe the model has all these probabilities, a whole tower of higher and higher order joint and conditional probabilities conditioned on more and more and more and more things, depending on more and more and more things. But maybe all of these high order ones happen to numerically agree with just the simplest ones, the ones that are conditioned on just one earlier time and tell you the next time. They're all there. All those higher order probabilities are there. They're just equal numerically to these lowest order ones. For a system like this, we have the feature that if you tell me what the system is, what its configuration is at any one moment, we can predict, at least probabilistically, and in some cases deterministically, what its configuration will be at later moments. And this is called a Markov system. It is very important to remember that for a Markov system, we still have all those other probabilities, all those second and third and fourth and higher, those more and more complicated conditional and joint probabilities. It's just that they are numerically equal to the simplest ones. And from the simplest ones, we can then predict the behavior of the system. Okay? And people just assumed that those were your options. Either you have a bunch of higher order conditional probabilities that are distinct, or you only have the lowest order ones. I guess there are other options, like maybe you have the lowest and second order ones, maybe you have the lowest second and third order ones. There are various levels of not being Markovian. You could be maximally non-Markovian, and then they're all different. But you could have second order non-Markovian or third order, where maybe the first and second and third orders are different, or you could just have regular Markovian, which is all that matters is the most recent time that you condition on and nothing else. And once you know that, you can then make predictions about the future behavior of the system. Now, I should say that for something like Newtonian mechanics is actually not quite Markovian. Newtonian mechanics, you have to know the configuration of your system now and at an infinitesimally earlier moment. Or equivalently, the configuration now and the velocity now, they're the same. And then with that, you can make further predictions.
Over the time dt.
Over time dt.
But you make that up, like you just make that approximation to make it Markovian.
That's right. What you do is you basically add to your configurations, either the configurations at a dt earlier, like an infinitesimal time earlier, or you add your configurations to velocity, and then you can pretend that the system is Markovian.
So you're saying even in Newtonian mechanics, it is non-Markovian, but just making a slight tweak, we just make it Markovian.
This is a trick known as constructing a hidden Markov model, taking a non-Markovian model and making it look Markovian by including some of that additional data into your present, what you mean by your present configuration. This turns out not to work so well if the model is infinitely ordered non-Markovian, because then there's just too much information to squeeze in. Exactly. Yeah. What people didn't seem to realize was that there are even simpler models than Markov models. Models in which we don't specify the higher order probabilities at all. They're not supplied by the model. It's not that we specify them and then equate them to the first order ones. We don't specify them to begin with. They're not provided by the model. And in fact, not even all of the Markov probabilities, the first order ones, are supplied. These models have simpler, sparser conditional probabilities, fewer. In particular, they fail to be Markovian, not because they have extra structure, but because they have less. And these models have come to be called indivisible stochastic processes, a term that goes back to the quantum information literature in 2006-2008 in a paper by Ignacio Chirac and Mikhail Wolf on quantum channels, but got its name referring to ordinary probability type processes in a review article in PRX Quantum from 2021, preprint 2020. It's open access. You can go read it, by Simon Mills and Kevin Modi. These processes are simpler than Markov processes. They have fewer conditional probabilities. And they fail to be Markov in the sense that you can't just pick any time you want and take that to be a conditioning time and then predict probabilistically what the system will be. If you want to predict what the system will be, you may have to go back to some previous conditioning time that is available. These conditioning times are called division events.
Okay.
And this means that these systems are not Markovian, but in a way that is more rudimentary than a conventional textbook non-Markovian system. And as best I can tell, these weren't studied because no one noticed them. People just didn't consider them until basically 5 years ago. I didn't read the literature on indivisible processes originally. I stumbled on them because I was trying to explain quantum theory in a class I was teaching. And I ended up trying to find a connection between stochastic processes and quantum theory. And I ended up realizing I needed these processes. I also call them indivisible. But then I went back and I discovered that just a few years later, the same name had been used for the same processes. In fact, the same symbol. I was using a capital Greek letter gamma to represent these processes. And it was the same letter that was being used in this review article. I was afraid I was going to be scooped, but the article didn't make any connection between them and quantum processes. The article noted in figure 6 that, I think page 15 or something like that they were a thing you could define, but then no further mention was made of them. And I felt a giant sigh of relief. Okay, no one noticed that these things are actually important.
Reminds me of David Bohm and De Broglie independently arriving at the same theory. Sorry, just while we're here, can I just take a quick digression, zoom in? You mentioned indivisibility and these cuts that you're making. what's deciding where you get to make this cut in this giant analog ocean of values that you could have?
That's right. So cuts is not quite the right word for it, and they're not done by hand.
Mm-hmm.
You simply let the process unfold, and at various times, division events will spontaneously show up. They show up when the system you're studying, the system you're looking at, interacts in the right way with another system.
So these are emergent divisions?
They're emergent divisions.
Okay.
They're not put in by hand. They emerge from how your system interacts with other systems.
Not fundamental.
They're not fundamental. They happen when your system interacts with other systems. If the other system interacts with the system in question in a way that where it develops what's called a classical correlation, an ordinary old-fashioned correlation between the configuration of the system looking at your system and your system. And the system looking at it can be anything. It doesn't have to be an observer. It could be just a particle. It could be just the simplest thing. When the right kind of interaction happens and you do a process called ordinary old-fashioned vintage marginalization, what you find is that the system you're studying develops an effective break in its evolution. The conditional probabilities develop another available conditioning time called a division event.
Okay.
And so these division events are just sort of popping up sort of more or less all the time. The more isolated a system is, the fewer division events it will have. If it's perfectly isolated, it won't ever have any. But for like a system that's very big, interacting with a big environment that's reading off its configuration, it's going to have rapid division events. And because it has so many of them, you can condition on basically any time you want, and you're going to return to the old kind of dynamics that we're familiar with, the old kind of dynamical laws that we're familiar with from pre-quantum physics. There's nothing fundamental about division events. We're not fundamentally saying that certain times are magically preferred over other times. This is more, all times are on equal footing. There's kind of a symmetry. One time and another is just as good. But because of the way that systems happen and interact, those interactions spontaneously choose or spontaneously break the symmetry in time.
Okay.
Just like you existing as an interesting geometric object and a person spontaneously break the fact that the laws of nature are fundamentally rotation invariant. The laws of nature don't care which direction you're looking at. The laws of physics work the same in any direction you can be looking in. But you, because you're not perfectly symmetric, you pick out a certain direction that's in front of you and a certain direction that's behind you and left and right. So objects pick out certain times. That's how these division events show up. Now, how does this resolve the measurement problem? There are no literal superpositions in this picture. Notice I told you the whole picture. I didn't say wave functions. I didn't say quantum states. No collapsing.
No.
It's not that systems get into weird superpositions where your system is both here and there, and we need some mechanism to collapse it to one or the other. It was never in a superposition, so there's never a need to collapse, and there's no measurement problem. The measurement problem simply doesn't happen. There's no fundamental wave function, so there's no debate over is the wave function a physical object or not a physical object.
No observer, no external
No
measurement.
special role for observers. Observers are just regular systems, and you can use the same analysis that Bohm used to work out the process of observing. There's a sense in which this is most closely similar to Bohm's pilot wave theory among the available choices, but without the pilot wave.
Not deterministic as well.
It's Bohm's theory originally was deterministic, although the attempts to apply it to quantum field theory tend to be indeterministic anyway.
Right.
But yes, it accepts the indeterminism of nature. It takes seriously what nature seems to be telling us. We do experiments. We see a unique outcome. The outcome appears to be probabilistic. There is reason to think that there is something inherently non-Markovian about quantum theory. There are, for one thing, there's a lot of work now on non-Markovian. You just Google non-Markovian quantum and you're going to find a million results. But there's a paper, I think, that codifies this rather beautifully by Glick and Adami that was published in Foundations of Physics a few years ago. This paper considers two ways to look at the process of measuring a quantum system. We have a quantum system, and we have a measuring device. And the measuring device is pretty small, well isolated. One way we can do it is have the measuring device make like n measurements in succession and treat all those measurements as unitary evolution without activating the measurement axioms. Let all n measurements happen with just increasing amounts of entanglement. And then at the very end, you, the external observer, come in and do one final measurement on the measuring device at the end and get the answer. That's option one. Option two is treat every one of the n measurements as a projective collapsing measurement. And you'll get different answers. between option 1 and option 2. It's like if you don't look at the measuring device in between, but only at the end, you get a different answer. And this is a distinctly non-Markovian behavior. So if we see things that look non-Markovian in quantum systems, I'm just saying take that seriously. Rather than look at all of these things and say, well, we see a definite result. It's probabilistic. Looks like only one thing happened. It looks like there's one copy of myself. But I'm just going to impose that the universe is in fact deterministic and there are many copies of myself. And I mean, it just seems like we're trying to hang on. I mean, when people talk about, oh, you're trying to hang on to a pre-quantum picture of the world. Determinism is part of a pre-quantum picture of the world. Demanding determinism at the cost of introducing zillions of parallel universes and all the problems of trying to make sense of how probability is supposed to show up, as one does in the Everett approach, to me that seems like a pre-quantum assumption to make on our theories.
I will concede that something about the universe being random or arbitrary or stochastic doesn't feel right. If we were talking about grounding and fundamentality earlier, it feels like there has to be a grounded layer below this probabilistic layer that's deterministic. Pierre Curie had put forward the Curie principle, which said that a particular result, that is the choice of one outcome among many equally possible ones, requires a particular cause. It's not good enough to say that one of the possible outcomes just happens. One must be able to point to a specific reason for that outcome to occur, as opposed to all the others. And I think Curie has some merit to this argument. Leibniz had put forward the principle of sufficient reason.
Exactly. Yeah.
Einstein has said God does not play dice.
Yeah.
Is it possible that, I know you just said that nature is showing us that it's probabilistic. Is it possible that there's a deterministic layer even below this stochastic probabilistic layer?
That's a lovely question. I'm going to put on my annoying philosopher hat now and respond by asking, what exactly do you mean by determinism? Okay. I said at the beginning of this conversation, near the beginning, that when you have a law that together with the starting conditions lets you predict exactly what a system is going to do, you have a deterministic model.
Yeah.
How complicated is that law allowed to be? Suppose I take my law to be the following. Let f of t be the state of the universe at time t, and my formula for f of t, the definition will be, take the actual history of the universe, the whole history of the universe, and select the moment t and spit it out of this function. Well, that's a mathematical law. It tells you what's going on deterministically, but it's rather complicated. The law is not a simple equation. The law requires inserting the entire actual history of the universe into it. This feels kind of like cheating. Like if I make my law sufficiently complicated, I can make almost anything deterministic. So let's suppose we take my picture, the picture I'm presenting here. At every moment, the system has some configuration, and there is at every moment a probability distribution for which it has that configuration, a standalone probability distribution. What we lack is simply more than a sparse set of conditional probabilities. We cannot assign joint probabilities in general to the whole trajectory. We can't assign a probability to an entire trajectory. Our conditional probabilities are somewhat more limited. But suppose that I simulate this system on a computer, and you can. This is a fairly easy thing. You can go to ChatGPT and ask it to, or Claude or whatever AI system you want, and ask it, write me code that will simulate a system with the definition I've given it, and it will give you code to do it. Not only can you simulate on a computer, but there are like realistic systems you can build that exhibit this kind of indivisible behavior. I have a couple in some talks. You can go, if people want to see some of the examples, go look at some of my YouTube talks. There's this one example with a thermodynamic system that provides the analog model for a single qubit, and it can be extended to describe multiple qubits. These are systems that are not truly quantum mechanical, but they just are indivisible processes, and therefore mathematically they have a Hilbert space picture that looks like qubits. So there are a lot of concrete examples already that you can write down that do this. So if your question is, well, can these systems really exist? Well, yes, they can. You can simulate them, you can build them. There are these systems. The question is, are quantum systems these systems? And I'm arguing that they are. But suppose you take the numerical simulation I just gave you. In this numerical simulation, the simulation knows the trajectory of every run of the system. In this simulation, you run the system, let's say 10,000 times. Each time you run it, you will get a particular trajectory. And you run it 10,000 times, you get 10,000 trajectories, and those trajectories by construction have to obey the dynamical probabilistic laws that we've specified for them. Suppose I take one of those runs, one of them, and I take the actual trajectory the system took in that one run. And suppose I take this run to be the whole universe. Suppose my simulation is so big and so powerful that I'm describing the whole universe now, and I have the exact path the universe has taken. That path can be expressed as a function. And I can take my law to be the configuration of the universe at time t is whatever that function says where we are on that path at time t. And you might object and say, yeah, but that path is going to be super complicated. Your law is going to be super complicated. And then my answer will be, but it's deterministic. It's just a very complicated law. In order for something to count as deterministic, perhaps we should agree that the laws should be much simpler than the entire detailed trajectory of the thing we're trying to describe. Otherwise, it's deterministic only in a very trivial sense. Yeah. But there is some trajectory. In any time you realize this process, at any time you simulate it, there will be some trajectory. There will be aspects of that trajectory that we cannot know. The computer knows what trajectory it was. We can ask the computer to tell us the trajectory, but if this were a real-world indivisible stochastic process, we wouldn't know the exact trajectory. We would be able to do experiments, and those experiments would create division events, which would give us conditional probabilities, and those would exactly agree with the predictions of quantum mechanics. But if you want to know more information, if you want to know about joint probabilities that are not connected to observation, we don't have the ability to do that. The theory doesn't supply us with those things. And that's the breaks. We don't get to know everything. Now, some might say that this is a criticism of this approach, that this approach contains some things that we don't have equations for. To which I would say, we're going to have to give something up. Quantum theory is not classical physics. Something's going to have to be given up. We don't want to give up empirical adequacy. That's a deal breaker. We need the theory to make the correct predictions in whatever situations we want to ask it to make predictions in. We want the theory to be unambiguous when applied to arbitrary kinds of quantum systems, like the kind, as I've said, that may occur in astrophysical or quantum gravity situations. We don't want to have to make an endless list of speculative metaphysical hypotheses, especially when, arguably, even that is not sufficient for making a theory work. But yes, there's this aesthetic issue that there are some things going on in the theory that we don't have equations for. But this is certainly an improvement over what we had before, because the textbook Dirac-Feynman axioms also don't give us those probabilities either. The Dirac-Feynman axioms only give us the measurement probabilities, which this theory supplies. So we have a theory that meets my minimal requirements. If you really badly want a theory that tells you absolutely everything, or a theory that's deterministic, we don't have any viable candidates for those right now, in my view. Perhaps someone will come along with a better interpretive framework, one that gives us equations for absolutely everything, and those equations are not extremely gerrymandered or complicated, and they work for all kinds of systems. Maybe there's a theory that doesn't have this gap that this indivisible stochastic approach has. That's why this quest to find the best way to think about quantum theory is not done and may still be continuing. But my view is that this is and should be the leading candidate for the way to interpret quantum theory. The remaining aesthetic obstacles aren't about infinite numbers of parallel universes that we can never directly see. And the theory appears to be empirically adequate. But there are some aspects of this theory, there's some aspects of reality that, according to this interpretation of theory, we simply don't have information about. That said, when you take these small ingredients and combine them into bigger and bigger systems, because of the way that systems interact with their large environments, we will get those probabilities. And eventually, when the system is big enough, we'll have a system that's obeying reasonably familiar-looking laws of physics. I'm willing to bite those bullets. Now, you said before this question of this Curie quote, Pierre Curie principle about the necessity of causes. So I'm going to be annoying again, and I'm going to ask you, what do you mean by a cause?
Oh, it's an open question.
Yeah. What do we mean by a cause?
Well, in this case, it would be the same deterministic rule, law that I'm considering fundamental.
Okay. If your definition of cause is a deterministic rule, well, then this theory doesn't have those kinds of causes.
Correct.
Is that a deal breaker? I don't know. It would be nice if we always had causes for things. In that sense, the deterministic law that always tells us what happens. But I don't know how much of a deal breaker that should be.
Do you consider indivisible stochastics to be an intermediate layer or a fundamental layer?
I don't know whether it's an intermediate layer or a fundamental layer. It could be there's a deeper, more fundamental layer. In particular, from a God's eye view, you know, if from a God's eye view, one can see the actual trajectory that the universe is truly taking. Just like in a computer simulation where we can take our God's eye view, we can actually see the trajectory that's happening underneath all of this. At some level, that's the fundamental view. Now, it may be that there is some simple equation that describes that trajectory that we just don't know yet, and maybe that would be a better theory than this theory. If that's the case, then this theory is an intermediate step, but it may also be the case this theory is the end of the road. This is the best we can do. I mean, after all, how could we empirically go farther than this theory? If you want to know the underlying trajectory, you'd have to go out and try to measure it. But in the measuring of it, you'll generate division events, and then this theory will tell you what the probabilities are that you should have for those things. So the very things that we want, apparently, that go beyond the indivisible stochastic approach are fundamentally empirically inaccessible. They can't actually be obtained. So it's unclear how we would ever even know whether an interpretive framework or theory had correctly given them to us. If every time you try to measure them, you get probabilities that actually the indivisible stochastic theory already provides, then how do we know what goes beyond it? There's an admission of our epistemic limitedness here. We're not going to propose things in this framework that we have no business knowing. Maybe you can propose a simple description for those things, one that's nice and elegant, and I would be very happy to see such a theory, but I don't know whether one is available, and I certainly don't want to wait until we find one. I'd like to proceed with something that works and does better than the other approaches right now.
I definitely see value in the theory, even if it's intermediate or it's fundamental, even if it's emergent. This is where I disagree with Scott Aronson. He said that he didn't see much value in moving from one probabilistic framework to another probabilistic framework. Probably what he was expecting was something that carves a path through this probabilistic domain. But I disagree. I completely agree. If you can actually reformulate the Bone rule and reformulate all of these these rules using classical probabilities and remove all
vintage probabilities.
This is where I'm going to patent it, and I hope it sticks. You never know about physics where these words take from, right?
Of course, yes.
So if you can actually use these vintage probabilities, if you keep saying it enough, it's going to stick.
Sure.
And get rid of all this baggage of the wave function measurement, entanglement, the observer, I do think it's a good exercise.
I mean, when you present this to students, I mean, look, ultimately you will have to teach them about Hilbert spaces and wave functions, but it's one thing to start with, okay, there are systems that can be in configurations and there are probabilities, and we know how probabilities work, and we work all that out and we have a picture. And then what we can do is through clear mathematical definitions, define the various ingredients of Hilbert space picture and get all the axioms out. Yeah. This is much clearer for a student than simply positing all these abstract axioms from the beginning with no underlying picture. So I think from an educational standpoint, for someone who has not already been spending 15 or 20 years working in quantum theory, I mean, I have tremendous respect for Scott Aaronson. We're friends. He's obviously brilliant and amazing, and is, does incredible work, obviously, in quantum computing and everything like that. So I take seriously all of his criticisms, which are very well taken. But I do personally disagree, because I think there is value in taking a very complicated, very abstract set of axioms that arguably have ambiguities in them and replacing them with much simpler axioms. Again, axiom 1 is that every system has a configuration in some set of configurations, and axiom 2 is that the laws are these sparse conditional probabilities. That's it. Ordinary vintage probabilities, right? I mean, that's much simpler, and it's a picture that's easier for example, students to understand, I think. And then from this, we can then define all those other ingredients and also see where those other ingredients break down and why. And we can now probe some of those questions. But what I've told Scott, and you mentioned this interview I had with Scott, but what I'll certainly tell other people, right, is that when you start with different beginning premises, you have different, conceptually speaking, metaphorically speaking, you have different knobs you can turn to modify or generalize or change the theory. And this is going back to Richard Feynman's Character of Physical Law lectures, right, where he talks about why it's useful to have different ways to formulate a theory. Different formulations may suggest different ways to generalize or modify or alter the theory. The Hilbert space approach has a very delicate relationship to probability. You have to go through many steps to get to probability when you start from the Hilbert space picture. If you just try to modify the Hilbert space picture in some arbitrary way, you risk damaging those steps and getting nonsense probabilities that don't satisfy even the most basic conditions the probabilities are supposed to satisfy. When you start with a theory where the theory is phrased from the beginning in the language of vintage probabilities, then you can modify the theory in all kinds of ways. And I presented a couple of those ways in my discussion with Scott. And you're still going to have a good probabilistic theory. You're not going to run the risk of those problems. That's a useful exercise. But I would also just say there are other things we want to use quantum theory for beyond quantum computing, where we may need a picture that's different in order to make unambiguous predictions about what's supposed to happen in these cases. Now, that's all for quantum theory, but the world isn't just made of people who use quantum theory. I mean, I know that academics can get the sense that we're the center of the universe, or whatever our discipline is the center of the universe, but it's not. There are people who are not using quantum theory. They're studying other kinds of systems. People working in biostatistics or statistical modeling or stochastic modeling, or people who are working in neuroscience, or people who are working in other areas of computer science, or people who are working in material science, or people who are trying to build next generation energy technology, or people. That's just in the sort of the physical and biological sciences. The people in all other areas. Economists, political scientists, who knows? Anytime you build a new set of connections between one theoretical framework and other theoretical frameworks, you don't just benefit from maybe understanding one theoretical framework better, in this case, quantum theory better. You open up the possibility that maybe you could either understand those other areas better, or use the connection to this first theoretical area, to quantum theory, to be specific, to make predictions or understand or model these other systems. I've already said that there are already examples of indivisible stochastic processes that you can just realize in computer simulations or in tabletop experiments, but there are also potentially examples that show up in epidemiology, or examples that show up in neuroscience, where maybe we have a system and we know very little about it, but at least we know a little bit of some sparse set of conditional probabilities for these systems. Suddenly, these systems may become amenable to using all the mathematical machinery of quantum theory, and maybe even quantum hardware, in the form of as yet to be realized fully working quantum computers, to model and simulate and make predictions about these non-quantum systems. So maybe that won't help the quantum computing scientists, at least not directly, but it will certainly help other people. Right? Whenever we make a connection between theories, sometimes people, so a classic example would be when Darwin was inspired by Malthus's work on economics. and the idea of scarcity and so forth to be inspired to come up with a new way of thinking about the origin of species and the development of life through natural selection. Connections between fields often have profound and unexpected consequences. They may or may not be realized immediately, but they may be realized down the road. And that's why I think it's always worth trying to find them.
I would love to zoom in on these connections between the fields because you work in the field of philosophy of physics. Historically, philosophy and physics were pretty much the same subject. Aristotle, Newton, Leibniz, Galileo, case to be made for Einstein as well. A good physicist was a good philosopher. There's no question about it. But now it seems these fields have diverged. And I've spoken to quite a few professors of philosophy of physics and philosophy of math as well on the show. And they have lamented the fact that these foundational questions in physics and math have in a way been outsourced or relegated to the philosophy department, and theoretical physics has moved away from it because you shouldn't ask these questions. These questions are quite metaphysical. And as a result, they've run into these contradictions because they've not solved the foundational questions. Do you see this divide existing between theoretical physics and the philosophy of physics? And if yes, how do you resolve it?
When you read the work of some of the greats of theoretical physics, you see a lot of philosophy. I mean, the character of physical law, those lectures by Richard Feynman I was talking about, make a lot of philosophical arguments about the way to think about science. I mean, literally metaphysical arguments not about physics exactly, but like how to think about it, how to do physics. I think a lot of physicists, so there's definitely some physicists who take philosophy very seriously. I know them and we talk about philosophy and it's great. They may not, use philosophy all the time, or they may not have devoted a lot of their time to learning the methods of, say, analytic philosophy or whatever, but they respect and they regard people who work in philosophy of science as important colleagues whom they go to and they talk about things with. And that's great. I know people like this. It's fantastic. I think there are some physicists who are kind of in denial that they're doing a lot of philosophy. They think that physicists don't need philosophers and don't need philosophy. And they may realize they're doing philosophy sometimes. They may not realize they're doing philosophy. And then, of course, there's some physicists who just really, really don't ever talk in a philosophical way. They just focus on getting results and so forth. I don't know why we've ended up where we have. There are a lot of theories with a small letter t, not grand like mathematical theories, just more like hypotheses. There are a lot of hypotheses, a lot of guesses for why we've ended up where we were. Historical contingency, the shift of physics from Europe to America, World War II, the appearance of large amounts of funding in physics, which have redirected physical priorities to much more realizable, practical kinds of concerns. I don't know or understand how we've ended up where we have. This may also just be the nature of academia, which is specialization. As academic areas develop, there's more and more to learn. People can't learn everything. They specialize more and more. And as people specialize, they get siloed. Ideally, when that happens, there's still a mutual respect that's maintained between disciplines. It doesn't devolve into our discipline is therefore better than yours. But I think there's a little bit of Sturgeon's law in effect here. So Sturgeon was a science fiction author who lamented the fact that some other members of the literary establishment looked down on science fiction, thinking that a lot of it was not very high quality. And his reaction to this was that they were right. Because yes, okay, so 90% of science fiction is crap. But only because 90% of everything is crap. This became known as Sturgeon's law. 90% of everything is crap. And when two fields are very close together and engage a lot, they can see the 10% that's non-crap in each other's fields. But as fields decohere into non-interfering branches, right, so to speak, it becomes harder and harder for people in those two fields to recognize the good 10%. They just now see what looks mostly like crap. And they think, therefore, the field is... And they'll point to lots of examples. They'll say, really? You think that this field is not junk? What about these 10 papers that just came out? They're terrible. But both fields can do this, right? And so I think lack of familiarity actually in this case is what breeds contempt. It's the opposite of familiarity breeds contempt. Lack of familiarity here breeds contempt. It's funny about contempt. It's bred both by lack of familiarity and also by familiarity. So I would say that what needs to happen is much more engagement. And I'm putting my money where my mouth is. When I teach my physics classes, I introduce a lot of philosophy. And when I try very hard to engage with colleagues on both sides. I mean, my training, my PhD training is in theoretical physics, but most of my work is in philosophy and in the intersection of philosophy and physics, or at least physics done using the tools of philosophical analysis. And I'm always trying to talk to people on both sides of the divide. And I'm trying to bring people together because I think that the fields will do better if they're closer together and can benefit from that 10% of the high quality stuff. Just like arguably they were benefiting from each other 100, 150 years ago during the development of some of the greatest physical theories we've ever seen. I've said this before, but one of the things that philosophy is very good at is sharpening inchoate questions into proper subjects of scientific investigation. This is, again, not the only purpose of philosophy, but it is one thing philosophy can be good at. Sometimes questions are too blurry to be subject to proper scientific investigation, and if philosophers can make them amenable to that, then that's helpful. And then people should remember that philosophers played an important role in, so to speak, softening the soil for empirical progress. I guess my feeling is, so some physicists, certainly historically, this has been the case, physicists in history, but even some today, even if they're not philosophers, they read literature and they use philosophy well. And some physicists who maybe don't know the philosophy very well or aren't trained make arguments that are philosophical but are not good arguments. And that doesn't help anybody. It's always better if the arguments are good, especially in areas of physics where we're lacking in experimental data and we're relying much more on logical analysis and reasoning to come to conclusions about things. This is exactly the situation in which you want more engagement, not less, with people who have been trained to be as careful as possible in their reasoning. Of course, they make mistakes. Everybody makes mistakes. 90% of the subject is crap. That's the way everything is. But when done well, there's a major contribution that's possible here. So what I would just say is, I think when there are physics conferences, they should invite some philosophers to come who have the requisite expertise in the subject, who can keep people honest, who can keep people from flying off into fairyland with some of the conjectural things that sometimes people like to do, that when people start stacking speculative metaphysical hypotheses one on top of the next, there's someone to say, wait a second, hang on, you gotta be a little careful there. What are you saying? Probability doesn't really work that way. Causation doesn't really work that way. Like, to hold people accountable, keep them honest. I think that there could be some real mutual benefit in both directions. And again, I'm living this, right? I take this very seriously. Some people who are watching this video may be physicists I've sat and spoken to for hours to make progress on bringing these fields together. I take that very seriously. I think it's a very important thing for us to do.
I want to talk to you about the role of beauty, which I think dances with both physics and philosophy. In a previous interview, you had said, I had a really amazing experience taking physics in 11th grade. There was something very elegant and clean about physics, in retrospect, almost platonic. There were these perfect entities, point particles, trajectories, magnetic fields, light beams, elegant thought experiments that seemed so much less messy and complicated than everything else I was learning about in my other classes. It was definitely that aesthetic element that drew me in, rather than a desire or ability to build useful things for the world. And I really loved manipulating equations. It was like formulating magic spells that the world mysteriously had to obey. Is there any other human endeavor like that? When we were talking about Indivisible Stochastic as well, you mentioned that this is a lot simpler, it's a lot more elegant. Is this an indicator that you're on the right path? Is it the right kind of a marker that nature, that reality is simple, it's elegant, possibly symmetrical, it's beautiful? Or do you think that's a trap physicists and philosophers can fall into?
I agree with everything you've said in both directions, in all directions. I think it draws us in. I think it's a good starting place. I don't think it's a good justification. I think beauty can inspire. It can inspire ideas. I think as an intellectual exercise, it's always nice to ask, can we build a theory that is beautiful? But beauty cannot justify the correctness of a theory. At the end of the day, your theory either has to be mathematically equivalent to theories that work well, or if not, the theory has to make predictions that can be verified in experiment, or some combination of both, or things like that. I mean, there are practical concerns that a theory has to have, but it's hard to guess theories. And for reasons that we don't fully understand, the patterns in nature, at least the most seemingly fundamental patterns in nature, the ones that so there's this question about fundamentality in nature. I mean, there are a lot of different levels of science. There are different kinds of sciences. And there's this question over whether all science is derivable from physics or not derivable from physics. Right. And these are very complicated debates, and I don't want to wade into them because there are partisans on various sides of these debates. I just want to say, though, that when looking at the kinds of models that we take to be fundamental in physics, and here I mean something very specific by fundamental, these are models that, although they can't necessarily be used to make predictions about very complicated systems or macroscopic systems, their behavior fixes what the rules are of those other systems. Once the standard model is in place, there doesn't seem to be any wiggle room for changing the rules of, say, a superconductor, right? Now, it may be that you can't use the standard model directly to predict what a superconductor will do, but superconductors are described by rules, and you can ask where those rules come from. Could they have been anything? Once the standard model has been fixed, as long as you agree to the extent that you're applying the rules of the Dirac-Vadman axioms and the standard model and all of that, there's no wiggle room to change those rules. That's the sense in which I think one can talk about one set of rules maybe being more fundamental than another. Although, of course, I take very seriously that physics is different at different scales, and I'm not saying everything is reducible to standard model. So no one assume I'm saying that. But what is interesting is that when you look at the most fundamental rules, they do seem to be elegant and simple and beautiful. And no one knows why this is.
Beauty is fundamental.
Maybe beauty. Paul Dirac, again, this is the same Paul Dirac, wrote extensively on the importance of beauty in physics. He said physical laws needed to be beautiful. Not simple necessarily. He said that general relativity, Einstein's theory of gravity, was not simple. It's a very complicated theory, but it was very beautiful, in some respects more beautiful than the simpler theory that Newton had proposed for gravity. But what exactly is beauty? I don't know. Philosophers have been debating what beauty is since well before Plato. Beauty is one of those things where we kind of know it when we see it. It's highly personal and highly subjective. I don't think there are any universal definitions of what kinds of things are beautiful. So I'm not sure I have much to say, except that I have my own standards for beauty. I happen to think that the work I'm working on seems beautiful to me. It may not be beautiful to everybody, but that's okay. I think beauty can be inspiring, but I don't think ultimately it can justify what we're doing as being correct.
I like it. Before we wrap up, I want to quickly touch upon some of the limitations with IST. You do use that acronym for it.
I don't really use an acronym. I just call it the theory of indivisible stochastic processes. Sometimes I'll call it indivisible quantum theory or indivisible quantum mechanics.
Okay. Maybe an acronym might...
Indivisible quantum theory, IQT maybe.
IQT. So we already touched upon one bullet that you were ready to bite, which is about the probabilistic nature of it. If you had to step into the shoes of some of the critics in Steelman, their case, what are some of the open holes that exist with IQT that you might want to work on in the future? And then maybe step back into your own shoes. How would you address these critics?
Well, there is what appears to be a precise mathematical correspondence. I call it the stochastic quantum correspondence between these kinds of systems, these indivisible stochastic systems, and quantum systems as described in the usual Hilbert space formulation. I don't know that there's really an opportunity for criticism there because it's just math. It's a mathematical correspondence. Where is there room for criticism? Well, a major problem is how to reconcile this picture with what people are trying to do in quantum gravity. So in special relativity, this will be a little bit technical, but in special relativity, we represent space and time with a picture called space-time. And all the points in this picture correspond to events that take place at a certain place at a certain time. And if you draw kind of like a surface, it's like a three-dimensional surface, which sounds like a contradiction because it's in a four-dimensional space-time. Three-dimensional things are called hypersurfaces. If you fix a particular moment in time, you'll get all the events that share that moment in time according to that coordinate system. And this is known as a space-like hypersurface that defines a particular moment in time. And once you're given a particular space-like hypersurface that corresponds to all the points in the universe at a given moment in time, you can talk about probabilities. What's the probability that various systems will be in various configurations on that hypersurface? Right. The indivisible stochastic approach to quantum theory then becomes a relationship between hypersurfaces rather than between times. In sort of a non-relativistic looking picture, we have conditioning on times. In a special relativistic picture, we have conditioning on hypersurfaces, spatial hypersurface, space-like hypersurfaces. Which hypersurfaces are picked out, it's just like for the non-relativistic picture, when environments come in, when systems interact with each other, they will pick out certain, not times, but certain hypersurfaces spontaneously. And then there'll be conditional probabilities that relate these different hypersurfaces. So the picture works reasonably well in this case. However, if you're going to allow the space and time, the so-called metrical structure of space-time to vary, as we do in general relativity. In general relativity, your space-time deforms. It exhibits what's called Riemannian curvature, and that Riemannian curvature is what changes the paths of objects through space-time and makes them appear to move as if there's a force pulling on them, gravity, when really they're just sort of following the shape of space-time. When you allow the shape of space-time to change, then you don't know a priori, that is, ahead of time, which slices are slices of constant time, which ones are space-like, which ones are not space-like. And if you don't know those ahead of time, it's not clear how to even write down conditional probabilities. So this whole picture appears to break down. And I think a critic could point to that. And of course, my response to that would be, yeah, that's a problem. Of course, it's a problem with all of our known quantum theories when they try to deal with gravity. General relativity, curving space-time, does not play very well with quantum theory when the curvature is significant. Now, in everyday life, gravity is pretty weak. And we actually have a really good working, effective field theory, effective quantum field theory that handles gravity, which makes predictions. People like John Donahue have a number of beautiful papers that talk about how this theory is supposed to work. It's only when gravity becomes very strong and curvature becomes significant that you're outside of sort of the regime in which we can neatly make the kinds of predictions we want to make. Or at very, very, very high energies where the gravitational field is so unstable that we just sort of lose track of what direction, time, and space are supposed to be. So we run into fundamental problems, but these are just the problems of quantum gravity. So this picture doesn't resolve, at least immediately, the problems of quantum gravity. So if your goal is, I'm not going to take on a new interpretation of quantum theory unless it solves quantum gravity, I'm afraid to say I don't have that solution yet.
Until I have a theory of everything.
Right, right. However, because we've rephrased quantum theory in different terms, this picture provides potential new avenues for modifying quantum theory to make it work with gravity. It may be very difficult. I mean, if the problem fundamentally is what does probability or conditional probability mean in a universe where you don't a priori know what you're... If you're trying to phrase everything in Hilbert's space picture, you're so far removed from probability that it's going to seem like a nightmare even to address this head on. At least in this picture, we're facing that problem head on. And maybe with a suitable modification to this picture, to these new axioms, we'll be able to accommodate quantum gravity in a better way. I don't know the answer to that question yet. What I do know is that a fully probabilistic version of general relativity is not yet in hand. That is not a version of general relativity where we treat the theory as non-probabilistic, as deterministic, and maybe add a few small corrections that are probabilistic called noise terms. No, I mean a fully probabilistic version of general relativity where we're facing head on like a generalization of general relativity where we're allowing the so-called metric tensor, the metric structure, the causal structure of space-time to be probabilistic. You'd think that that would be a natural step before trying to do quantum gravity. But this just vintage probability version of general relativity has yet to be developed. You'd think that would be the first thing to do.
That would be the link.
Right. And there are historical reasons why this wasn't developed. General relativity came very, very, very early on, and a lot of this probability stuff came later. And just because of historical contingency, people just never worked on this. People working on quantum gravity before we even had a proper theory of stochastic processes My strong speculation, and this is just a total speculation, is that if we had that probabilistic theory, it would either tell us a lot about what quantum gravity is supposed to be, or could even be quantum gravity.
This is your hot take.
This is my hot take. It could be completely wrong. I'm trying to be as careful as I can to separate things that are just speculation from things that are hot takes. But at the very least, this inspires, I think, maybe some potential further work. I think one criticism could be that a theory should not have any ingredients in it that we can't attach equations to. And I don't have an answer to that except to say I think this is still better than everything we have going for us. And it's certainly simpler, and it provides all these possible generalizations, and it provides all these potential tools for other disciplines to make use of, which maybe will feed back and tell us something more about quantum mechanics. Every time you build these bridges, you help other fields, but sometimes those other fields come back and help you in the end. So, and then finally, I would just say I think it's easier to teach this subject to students. I've said all these things before. What other criticisms are there? Well, there's a lot of work to be done. This indivisible stochastic approach has not been applied to a large variety of concrete physical systems to see how it really plays out. That's work that needs to be done. I'm only one person with limited time. If people watching are interested, this is a whole collection of projects people can work on. Like I've been saying, it's a blank page, and there aren't many totally blank pages that one gets in well-trod territory like quantum physics. So try applying it to concrete real-world models in physics and not in physics and see what you find. I think one criticism is that hasn't been done yet. And the answer to that criticism is, let's do it. Let's do it. This is very new. It's of very recent vintage. Let's see where we can go with it. I should have more criticisms of my own theory than I do, but I guess at present I don't.
I don't have a criticism, but I do have an insight. I did see a lot of echoes with Wolfram Physics, and I know we spoke about this earlier. I highly recommend that you do check it out because there are a lot of similarities and echoes in his model and Stephen Wolfram's model. There's this structure called a hypergraph with a lot of nodes, and they have connections with each other. And from this deterministic Rule-Liad, the sample space of all the connections, there's an emergent probabilistic layer. And then he has an element of both indivisibility and a non-Markovian feature, which he calls computational irreducibility, that you cannot predict the future state from just the present state. You have to simulate the outcome. So maybe it's not a criticism. It's just maybe you might find some areas of overlap with the two.
I'll take a look. Let me give another collection of possible criticisms. So another collection of possible criticisms is over the question of non-locality. So I'm going to say a couple of controversial things right now. Let's be a little controversial.
All the hate mail I'm forwarding to you.
Sure, of course. I mean, it's controversial, I think, in some sense, but maybe not as strongly. So I have read, I think, most of what John Bell has written, and I think John Bell is fantastic. I mean, I think that's unquestionable. Creative, clever, open-minded, and has in many ways moved science forward. John Bell was a particle theorist who did all this work on quantum foundations kind of behind the scenes, kind of, not in his day job, because he was doing a lot of it at a time when it was difficult for one's career to work on these topics. So he was a real path breaker, and it was an inspiration to many people. But John Bell was also a person. He was just a person. He was a very good person, but he was just a person. And I think there's a kind of deification that sometimes happens in different academic disciplines with certain people. There are whole conferences, conference after conference, the John Bell conference, the John Bell this, the John Bell that. And you go to talks where people just talk about John Bell over and over again. They write books about just John Bell, John Bell, John Bell. I think he would have been embarrassed to have been treated this way. He made major contributions, but the things he said weren't perfect. His famous theorem, Bell's theorem, he seemed, I mean, I've read the papers. I've read all the various papers he's written on his theorem. He kept altering the premises of his theorem with each paper, from the 1964 paper to the 1975/76 paper to 1990, just before he died. He just never quite seemed satisfied with his premises. The theorem didn't quite seem done to him. And again, this is a case where I'll say the very fact of his brilliance and his inability to close the deal on this theorem is evidence that something is not quite right with it. And I've argued in one of my recent papers, this is New Prospects for a Causally Local Formulation of Quantum Theory, that there is in fact something not quite right with Bell's theorem. Bell was trying to pin down a particular kind of non-locality that was a problem that quantum theory suffered from. The issue was exactly what kind of non-locality we're talking about, because there are harmless kinds of non-locality, like ordinary, old-fashioned, vintage statistical correlations between things. I mean, things are correlated at great distances, and we're not usually worried about this. And then there are more problematic kinds of non-locality, like a force exerting an action at a distance, like Newtonian gravity. Newton's old theory of gravity before Einstein was a force that instantly reached across all distances. There are many, many different kinds of locality/non-locality. There's action at a distance, there's statistical non-locality, there's what's called microcausality, which is a certain technical property that quantum fields are supposed to have. There's cluster decomposition. There's signal locality versus signal non-locality. Can you send controllable messages faster than light or instantaneously? Like, there's like a whole list of different forms of locality or non-locality. Quantum theory is signal local. There's a theorem, the no signaling or no communication theorem, that guarantees you cannot use any of the weird seeming non-locality of quantum theory to send signals. Quantum theory is certainly not statistically correlationally local. It exhibits non-local correlations, but those don't seem to be a problem in other theories. The question over whether quantum theory exhibits a problematic form of non-locality is the sort of thing that Bell was concerned with. And not just Bell, but Einstein, Podolsky, Rosen, various people over the years. And the kind of this question over like non-locality, non-locality, causal non-locality, this was the central topic of this work. The problem is that causation is really difficult to define. I asked you earlier in this discussion, you said cause, and you said, oh, by cause, I mean a deterministic law. Okay, that's one definition you could take of a certain kind of cause. When a thing happens and a deterministic law is summarizing or governing why that thing happens. But that's not the kind of law, that's not the kind of causation that Bell was concerned with, or EPR. They were concerned with whether a person doing something here can produce a cause that then has an effect over there. Right. The problem is that we don't have a good, rigorous definition of what this kind of cause is. There are many theories of causation, and Bell helped himself at various points to different kinds of either theories of causation or different hypothetical downstream implications of different theories of causation, but he could never pin down one that he was totally satisfied with. He needed a definition of causation that was both reliable and robust, and also implied that quantum theory violated it. In the sense of, so a definition of, I should say, of both causation and local causation that were reliable and that were violated by quantum theory. And he had this sort of problem that, to the extent that he could write one down that was credible and rigorous, quantum theory didn't violate it. And to the extent that quantum theory violated it, it was a version of causation that was either not rigorous or a little suspect. His first paper in 1964 helped itself to what's called interventionist causation. And I've talked about this in other interviews. Given time limitations, I'm not going to go into detail about this, but this is a particular theory of causation in which you need agents and measurements or interventions. So it sounds a lot like the same kinds of measurement problems you have with quantum theory. And if you want to build a physical theory in which there's no special role played by observers or agents or interventions, just atoms and the void, just atoms bouncing around, it's going to be very hard to formulate what you mean by this form of causation that way. And to his credit, Bell, in his 75-76 paper, The Theory of Local Beables, and in his 1990 lecture, La Nouvelle Cuisine, moved beyond interventionist causation. And that is to his credit. He clearly recognized this was a problem. But he didn't provide another theory of causation. He just said, I don't know what the theory of causation is, but I'm going to say that it should have this certain consequence. And in his 1975-1976 paper, he took that consequence to be a form of Reichenbachian factorization, a certain kind of factorization property. That came under a lot of criticism by a lot of people over the years that followed. Is that really a reliable principle? Are we sure it even holds in all cases in the macro world? Why should we assume that quantum theory should obey it? And if quantum theory violates it, does that just mean quantum theory just doesn't obey this weird principle? Does it really mean quantum theory is violating local causality? And in 1990, he had a different criterion. It's subtly a little bit different, and I don't quite capture this in the New Prospects paper. But Joanna Luke just wrote a paper in which she examines this difference in his premises and going to the 1990 article very beautifully. Rather than trying to locate his common causes in the overlap of two past light cones, he tries to locate them in a slice of space-time that completely covers one of the observers. The problem is when you do that, then you can't assume the observer's making free choices anymore, because if you completely cover their past light cone, then everything they do in principle is determined by what has happened in their past light cone. So he kept moving around his premises trying to find ones that worked and couldn't find ones that were both reliable, like I said, and also clearly violated by quantum theory. So this is a bit of a heterodox view, but I take the view that the question of causal locality or local causality in quantum theory is still open. I provide a candidate theory of causation in the New Prospects paper, built out of these conditional probabilities, which clearly set up relationships between conditioning things and target things, just like causes and effects. And if you try to build a theory of causation out of these kinds of ingredients, you can now more precisely specify what we mean by local causation and show that quantum theory satisfies it through an application of what is essentially just the use of the no signaling theorem again. That now we build a very close connection between signaling and this notion of causal locality in quantum theory. I'm not saying this is the final word, and some people criticize this. There's one criticism is maybe this is not the right way to think about causation, in which I would just say, then give me a better way. Give me a rigorous theory of causation that doesn't rely on observers and agents. Now, one criticism people will say is it's fine to rely on agents and interventions. I just disagree. And I think it's up to everybody to decide to what extent they disagree. It is certainly the case that if you rely on certain notions of local causation, maybe ones that are based on interventionism, then you can derive certain inequalities that quantum theory violates. And that's certainly a statement. It's telling us something about quantum theory. Quantum theory is not consistent with certain versions of local causation, and quantum theory is not consistent with Reichenbachian factorization. And that's an interesting property. It's not consistent with Bell's definition of local causality. That's a property quantum theory has. But whether that's a dangerous or deal-breaking property, I think depends on how seriously you take those criteria as the true best way to think about local causality. Nonetheless, I think that is a valid criticism one can make. And people will have lots of special examples. People will say, there's this discussion forum on physics forums that's been going on for some time. And the people there are clearly very smart and have thought a lot about physics and quantum mechanics, and they've read these papers and they've seen some of these talks. And they're having discussions about things like, is this the right way to think about locality or not the right way to think about locality? And I just love that they're doing this, because this is exactly the kind of work that we should all be doing. We should be thinking about how are we supposed to define things like locality? And there are conversations about, is this picture compatible with remote entanglement swapping or various different ways to think about locality? And arguably it's compatible with all of these things, and you just have to carefully write it all out as a process and treat everybody like atoms and not have humans intervening, and you can't invoke measurements or collapse anymore because those aren't really happening. Just play the whole thing out and just see it as it develops. And without being able to actually do projective measurements, there's not going to be the kinds of strange non-locality that appears to be happening. But maybe I'm wrong, and that's fine. But I think that the fact that people are actually discussing this is a good thing, and I hope people will do it more.
I hope so too. And I hope conversations like these continue those discussions. Let's start wrapping up. Before we go there, I would love it if you can interpret what masterpieces I've built with the Lego to accompany this wonderful cat that you built before the conversation.
Oh, thank you. So I'm going to take the easy way out and say they remind me of Escher sketches, MC Escher sketches. Yeah. This reminds me of some of his impossible figure sketches where he has cubes or Penrose triangles that kind of self-intersect in very strange ways. I think this is like the Hotel Belvedere was the name of what this reminds me of. I guess this kind of looks like one of the characters or robot or spaceship things that shows up in old video games. This reminds me of some of the old video games I used to play.
See it.
Yeah. And this just looks like a very interesting instrument panel. It's with a big red button. It reminds me of that meme where where there's the guy and he's looking at the button. He's like, should I push the button or not? And the button is something very obvious. Yeah. Like, push this button so that you can eat today. And the guy's like,
he's sweating.
He's like, should I push the button or not? Right. So yeah, this is all really neat.
The perfect collection. Oops, my Escher sketches. Last 3 questions. Recommendations from you. What are some books, movies, role models that have strongly influenced you in your life?
I classify my role models in a couple of different ways.
Okay.
They're the people who are role models for me as human beings. And because it's really hard to get to know somebody, I tend to limit this to people I have known very well. So these include some of my teachers. Douglas Bartell, my physics teacher. Hello, Doug. I'll send you a link to this.
He's watching. Yeah.
And other people who in school who played a big role for me. I mean, even my computer science teacher in high school, we were super close, and he used to. I once got in trouble because I was trying to hack into the school computers. And
as we all do.
Yeah, and he told me not to do it, but he was smirking the whole way through, which was like the nicest thing that. Yeah. That's Peter Grabowski, who was very inspiring to me as well. I'll make sure he gets a copy of this. So these are people that I knew well coming up through my education. When I was a little kid, I played a lot of chess, and I won some national championships. You can read about this on my CV, I guess. Maybe I'll even send you a picture of me at 4.5 holding a trophy at one of the nationals. And I went to a school in New York City where there was a chess program. It was considered a helpful kind of enrichment for kids. And the person who ran the program was named Svetozar Jovanovic. He was our chess coach, and he was a lovely person and had a huge impact on me. He liked to say that I was never going to have a future as a serious competitive chess player because I played too scientifically and I lacked a killer instinct, which I think is a fair thing to say about me. I like tactics. He said I was very good at tactics. But chess did help me a lot. When I approach a problem in physics or in philosophy, I see it very much like I see a game of chess. Like, to me, it's a very visceral kind of a feeling. Like, I look at it and I see a bunch of ingredients laid out in front of me, and I need to study them and understand them. I need to read the board and understand what's going on. And when you confront a chessboard, no one explains the board to you. You have to explain it to yourself. You have to figure out what's going on in the board, and you don't have any instructions. You have to have a plan, a goal, something that you want to accomplish. You're not supposed to play aimlessly. And to achieve that goal, you have to set up a series of steps. You have to make a plan. You have to work out what you're going to do, and it has to be an airtight plan so that your opponent can't interfere with the plan or mess it up. At the same time as you're developing this plan, you have to think about all of the things your opponent could be doing. You have to be aware of all of your weaknesses, the weaknesses in your position or in your plan. You have to anticipate them and explain, defend yourself against them in some way, explain them. And it may be that you have this beautiful goal and it's just not achievable. And if you have a beautiful goal and it's not achievable, you don't try to do it anyway, right? It's not like in chess, if you see a goal and you just really want to take that piece, but there's just no way to do it, you proceed anyway. You have to deal with reality. If a certain goal is unachievable, you have to shrug your shoulders and look for a different goal. And once you're done, once you've found your goal and you've found an airtight plan and you've defended yourself properly, you've constructed, in chess, a strategy, and in a physics or philosophical problem, an argument. And so when students, for example, ask me how to write a paper in philosophy, I often say, think of it like that. If you've ever played chess or imagined playing chess, think of it along some of those terms, breaking it down into all the pieces, having a goal, figuring out what your plan is, anticipating all the problems with your plan, shoring them up, but also being realistic about what your goals are. So that's really helped me a lot, so that's actually been a formative part of, I think, my education. When I was in college, I had an amazing mentor, Alan Blair, who helped run the undergraduate program in physics. He also ran a science program for high school students that I participated in at Columbia University, where I was. It was near where I was growing up in high school, and eventually where I went to college. I went to Columbia University, and he's just a wonderful person, and I got to know him very well, and he was always an enormous source of inspiration to me throughout my time in college, and I think the world of him, and I hope he sees this too. So these are people I knew very well, and of course my family and friends, and I mean they're incredible people. I'm very inspired by the people I've gotten to know here at Harvard. Harvard is an institution like none other. And having been here as long as I have, I'm aware that it is a highly imperfect institution. That goes without saying in many respects. It's sometimes very frustrating in a lot of ways. But Harvard is made of people. And the people are some of the most incredible people I've ever met in my entire life. I think about the people I've met here in my time here, the friends I've made, the colleagues I've made, and they all know who they are. If any of them are watching this, they know because I tell them all the time, repeatedly, that I think the world of them, that I feel grateful to have ever gotten to know them, and they inspire me. They're my role models. So again, this is one class of role models, people I've actually gotten to know who've inspired me. Then there are role models that are somewhat more removed. And for them, I want to be a little more careful because I don't really know them as people. Maybe they did things that are really not good and I wouldn't agree with, but maybe there are certain aspects of things they did that I think are really amazing. I love the fact that when Dirac was describing how he would develop physics, he used to say he would just play around with equations. He wouldn't always have a goal in mind. He would doodle. He would just start deforming his equations and manipulating them, doing things with them, sometimes things that were not legitimate. And sometimes he would discover that they were in fact not legitimate. And sometimes he would discover clever things you could do that opened up the door to new things. The story of how he discovered the Dirac equation is kind of an amazing story in that regard, I think, among many other examples. So just being playful about how we approach physics, I think, is really lovely. The way that Einstein did physics, in many ways borrowing from the tools of philosophy, given that he was highly trained in philosophy, starting from when he was in high school, that's, I think, a source of inspiration for the kind of work that I'm trying to do. I think one figure I'm just deeply enamored with is Greta Herrmann. So Greta Herrmann was one of Emmy Noether's students. Emmy Noether is also another figure I'm just super amazed by and inspired by. Let me quickly say about Emmy Noether, because I think some people listening may have heard of her and some people may not. Emmy Noether was a mathematician who lived in the late 1800s and early 1900s. She had a difficult academic experience because she was a woman and also Jewish at a time when it was very difficult to get employed at various points because of that. She was a brilliant mathematician. Many of her biggest contributions were in an area of mathematics called group theory and abstract algebra. In 1915, around the time when Einstein was finishing up general relativity, David Hilbert, a mathematician at Göttingen, was very confused about how conservation of energy was supposed to work in general relativity. He ended up handing the problem to Emmy Noether to solve. And in 1918, she published two theorems, the two Noether theorems, the first of which is the more famous, I think, in a lot of ways, although I guess we use both of them at various points. I would argue, I think it's arguable, I think you could take different views on this, but my view is that Noether's theorem is the most important theorem in physics. It is the most unifying theorem. It shows up in so many different places and so many different theories. Noether's theorem sets up a connection between symmetries of laws That is, when your dynamical laws themselves have certain symmetries to them, and things that are conserved quantities, conservation laws. It sets up a beautiful mathematical correspondence between these things. It means if you know your theory, the laws, the dynamical laws of your theory have certain symmetries, you can predict that certain quantities will be conserved. And it also means that if you experimentally discover that there are certain conserved quantities, then you can read those backward and infer symmetries that your laws must have, which can help you discover new laws of physics. If you don't know the laws of physics, but you measure enough conserved quantities and figure out what symmetries you need, sometimes there's enough symmetry to pick out exactly what the laws need to be. And this is in large part how the Standard Model was constructed. So in terms of like constructive power, her theorem is second to none. And she was an incredible person. I mean, she had an incredible spirit. She was apparently very optimistic. And ultimately, when she had to leave Germany because the situation became too untenable, she moved to Bryn Mawr and was apparently a very inspiring figure over there. Unfortunately, she died way too young. So she's, for me, just an incredible, inspiring figure. I mean, she wasn't even a physicist, and she proved the most important theorem in physics. She just swooped in and solved this problem. One of her students was Greta Hermann. Greta Hermann eventually moved into philosophy. She became a neo-Kantian. She was well-versed in quantum mechanics and wrote a whole collection of brilliant papers on quantum theory in the 1930s. One of those papers was actually on determinism and causation in quantum theory. It's a paper we read in my class on philosophy of quantum theory that I teach here. And in that paper, she, among other things, proposes a very interesting thought experiment, a quantum thought experiment that is very similar to the kind of thought experiment that shows up in the Einstein-Podolsky-Rosen paper later in 1935. And her papers were certainly read at the time. She also found a flaw in a theorem by John von Neumann, a theorem that was purported to have ruled out the possibility of hidden variables. She found a flaw in the theorem. The flaw that she found wasn't widely recognized for decades. John Bell independently rediscovered the same flaw, and eventually Greta Hermann's work was recognized. Greta Hermann eventually left academia to fight in the resistance against the Nazis. Later in her career, she survived the war, and later she returned to academia. I just think that's an incredibly inspiring story. So yeah, these are examples of people I've been inspired by, like actual human beings. I've already mentioned some poems earlier in this discussion. I think poetry is really a remarkable way to capture things that are maybe difficult to capture in any other way. My favorite poets are Emily Dickinson. Emily Dickinson is certainly my favorite poet. There are several of her poems that I just recite, like we send the wave to find the wave, an errand so divine, the messenger enamored to, forgetting to return. We make the wise distinction still, so ever made in vain. The sagest time to damn the sea is when the sea is gone. I particularly like that one. To me, it evokes how in quantum theory, we're very limited in how we probe nature. We send the wave to find the wave. We have to use what physically is allowed to probe nature. We can't gain access to information that we shouldn't have. It somehow captures that for me. But she also has written just delightful short ones like faith is a fine invention for gentlemen who see, but microscopes are prudent in an emergency. I happen to like that one. I'm also a fan of Whitman. When I Heard the Learned Astronomer is one of my favorite poems.
Right.
Where he talks about how for me, it gets across this idea that on the one hand, there's our mathematical descriptions of things, but they're not to be confused with the things themselves or what makes them extraordinary. At the end of the poem, after hearing this astronomer go on about charts and figures, he goes outside and looks at the stars. And his experience of actually witnessing the stars is different, and I completely agree. And to me, that is like 100%. Like, the world is not mathematics. These things are not the same thing. And I'm also a fan of Auden. One of my favorite Auden poems is The More Loving One, right? It has he talks about looking at the stars and wondering, do the stars, I look at the stars maybe don't care about me. If they did, but I didn't care about that. He talks about all this stuff. And he has this line in there where he says, if I think if equal affection cannot be, let the more loving one be me, which is just such a delightful thing, right? Like, whether it's people or the things we're studying, sometimes affection's not equal, but I certainly hope to be the more loving one. And there's this other poem he wrote, September 1st, 1939, which has this line, "We must love one another or die," which I think, especially these days, is something that I think we should all take seriously in mind. Yeah. And for movies, let me just say my favorite movie. Okay, so this is my favorite movie, Amelie. Amelie is my favorite movie. If you haven't seen Amelie, you should see it. But Amelie is my favorite movie for a lot of reasons. One of which is that when I was falling in love with my wife, she was living in France, and so that movie is very much about Paris. And whenever I see it and I listen to the music, it brings back a very special time in my life, and in both of our lives, my life and my wife's. So that movie really, it means a lot to me.
I like it. Final question, and the easiest question of all time. What is the meaning of life, Jacob Barandes?
So I had a colleague here, Rob Hart, who headed up our instrument labs, our teaching laboratories. And he walked into the room at the end of one of my classes. I had been lingering after class with a student, and the student had just asked me that question. What do you think the meaning of life is, Jacob? And Rob walked by just as the student asked the question. He didn't hear the question, so I said, Rob, this student just asked me, what do I think the meaning of life is? What do you think the meaning of life is? And without hesitating, Rob said, I'm not quite sure, but I suspect it has something to do with simple harmonic oscillation.
Okay.
Now, for those of you who haven't spent a lot of time in physics, that may seem like an odd thing to say. But when you study physics, it feels a lot of the time like you're just studying the simple harmonic oscillator over and over and over again. In your classical physics classes, in your quantum mechanics classes, in your electromagnetism classes, in your statistical mechanics classes, in quantum field theory, in string theory, in almost everything. It's this incredible workhorse system that shows up again and again and again and again, over and over again. And many complicated systems can be turned into harmonic oscillators. So when I teach about the Newtonian orbital mechanical problem, why planets go around the sun in ellipses, why in general paths of objects, planets, comets, asteroids, are what are called conic sections. There's circles, ellipses, parabolas, hyperbolas. One way to solve the problem is to do a mathematical trick that turns it into a simple harmonic oscillator. So, it's a trick that just keeps paying dividends forever. And so it actually surprises me a little bit less that he would say that. Maybe the meaning of life really is simple harmonic oscillation.
Maybe it is. Professor, if people want to connect with you, if they want to find out more about you or your work, what is the best way to find you?
Well, if people have questions about this project, people can email me. My email is pretty easy to find. Just Google it. What I will say, though, is that I get a lot of email, and so I may not be able to respond to people's messages. If you want to get a response to me, the best thing you can do is actually read my papers and ask a question that is informed by being familiar. I'm more likely to spend time and answer those questions, just because if you want me to do work, you should also do some work. But I don't respond to proposed new theories. In the academic community, people receive many, 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 many emails from people who have not studied a lot of physics and want to leap immediately to finding the unified theory that unites gravity and quantum mechanics. And what I'll just say is, if you're interested in physics, you need to study it. There are no shortcuts in this business. It does take years, and it's not fair that some people have access in their lives, maybe financially, just time commitments to be able to study physics. I know that's not fair. But there just isn't really a precedent of people in the modern era coming up with important new physical theories without doing the requisite training, which does take years. And we do get a lot of these email messages, so unfortunately, I cannot reply to them.
Professor, this is probably the 10th or the 15th episode I've done on physics, theoretical physics, quantum mechanics. I must say, no one has articulated the problems and the foundations as well as you have. I'm envious of the students who get to attend your classes. I wish I could have been one of them, but this has been a fantastic conversation. It's been the longest I've ever gone, and it's been a breeze. It's been more than 3.5 hours, but it's been truly a pleasure. I appreciate it so much.
Thank you. May we shake hands? Is that good?
We may.
That's great.